Yesterday morning, October 29th, 2025, at exactly 11:47 Coordinated Universal Time, something happened that we couldn't see. An interstellar visitor. 3ER Atlas reached its closest point to our sun, hidden perfectly behind our star, like a card player keeping their hand close to the chest. For the first and only time in its journey through our solar system, it was completely invisible from Earth's view. Here's the paradox that should make you pause. This object traveled for potentially billions of years across the void between stars and the single most important moment of its passage. Perihelion, when solar heating peaks. When any comet would reveal its true nature happened in a perfect blackout window. No telescope on Earth could track its movements. No observatory could capture what transpired during those critical hours. The promise of understanding this moment is staggering. If 3I Atlas is simply a natural comet, we're witnessing rare interstellar chemistry that teaches us about alien star systems. But if it's something else, something we've never encountered, then October 29th might mark the day everything changed, whether we were watching or not. The proof is in the data. Real spacecraft, NASA's Parker Solar Probe, ESA's JUICE, NOAA's GOES 19 satellite, all captured observations. The object brightened unexpectedly. Its chemistry showed anomalies that mainstream scientists acknowledge as unusual. Multiple space agencies activated special observation protocols. These aren't conspiracy theories, these are documented facts. But here's the question that lingers as we drift towards sleep tonight. What if the most important moment in human history happened while our view was blocked? What if we missed something we were meant to see? Or perhaps more unsettling, what if the timing wasn't an accident at all? Disclaimer. Tonight we'll explore real science about 3I Atlas actual observations, genuine anomalies, and mainstream scientific debate. We'll also carefully examine speculation always clearly labeled about what these observations might mean. Some scenarios we'll discuss are thought experiments, what-ifs, meant to stretch our imagination while respecting the boundaries between evidence and conjecture. This is the story of humanity's third confirmed interstellar visitor. The mysteries it carried, and the questions it leaves hanging in the December sky as it approaches its closest point to Earth. Let's begin. On July 1st, 2025, astronomers at the Atlas Telescope Facility in Rio Hurtado, Chile, spotted something unusual moving through the constellation Ophiuchus. It appeared as a faint smudge against the backdrop of stars, magnitude 17, far too dim for amateur telescopes, but bright enough for professional survey systems designed to catalog near-Earth objects. Within hours, the Minor Planet Center received the preliminary data. Other observatories quickly confirmed the detection. The object was moving fast, remarkably fast, and in a direction that immediately raised eyebrows among orbital dynamicists. This wasn't following an elliptical path around our sun. Its trajectory was hyperbolic, which means one thing with absolute certainty: it came from somewhere else. The mathematics of orbital mechanics are unforgiving and precise. When you plot an object's position over time and calculate its velocity vector, the shape of its path through space tells you everything about its origins. Elliptical orbits are closed, loops objects gravitationally bound to the sun, destined to return again and again in predictable cycles. Parabolic and hyperbolic orbits are open curves, objects with enough velocity to escape the sun's gravitational embrace entirely. 3I Atlas, officially designated C2025N1 Atlas, and given the interstellar prefix 3I as the third confirmed visitor from beyond, was clocked at approximately 68 kilometers per second relative to the Sun. To put that in perspective, Earth orbits at 30 kilometers, the fastest spacecraft humans have ever launched. Parker Solar Probe tops out around 190 kilometers at perihelion, but that's with a massive gravitational assist. 3I Atlas was sustaining its speed across interstellar distances, carrying momentum from whatever stellar neighborhood launched it into the cosmic void. The preliminary size estimates based on brightness and assuming typical comet reflectivity suggested something between 5 and 20 kilometers in diameter. That's enormous by interstellar object standards. Our first visitor, Oumuamua, discovered in 2017, measured maybe 400 meters long. Our second 2I Borisov in 2019 was perhaps 1 kilometer across. 3I Atlas dwarfed both of them by orders of magnitude. By July 2nd, multiple observatories had confirmed something crucial. This object wasn't just a rock tumbling through space. The Nordic Optical Telescope, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope on Mauna Kea all detected a diffuse coma surrounding the central nucleus. Gas and dust were streaming away from the object, creating that characteristic fuzzy appearance that defines comets as distinct from asteroids. David Jewett and Jane Liu, veteran comet hunters who've studied these objects for decades, confirmed that 3I Atlas was clearly active with cometary features. This was exciting news scientifically. 2I Borisov had been active too, showing water outgassing similar to solar system comets. But Oumuamua had remained stubbornly inert, leading to years of debate about whether it was actually a comet at all or something else entirely. The spectroscopic observations began immediately. When you point a spectrograph at a comet and spread its light into component wavelengths, you're reading its chemical signature. Different molecules absorb and emit light at specific frequencies, creating a barcode of dark lines and bright emission features that reveal composition. The initial spectra from early July showed exactly what you'd expect: evidence of dust, creating that characteristic reddish color from organic compounds called tholins, plus hints of the usual volatile ices that drive cometary activity: carbon monoxide, carbon dioxide, water. The standard ingredients of comets formed in the cold outer regions of planetary systems. But there was something unusual in those spectra, something that would become more pronounced and puzzling as observations continued through July and August. NASA's Hubble Space Telescope captured its first images of 3I Atlas on July 21st from a distance of 277 million miles. The images revealed incredible detail: a teardrop-shaped coma brighter on one side than the other, with what appeared to be a tail of material streaming behind the nucleus. Because Hubble was tracking the fast-moving comet background, stars appeared as streaks in the long exposure images, creating this beautiful sense of motion frozen in time. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its instruments toward 3I Atlas on August 6th. JWST excels at detecting the heat signatures of molecules, particularly in the infrared spectrum, where water, CO2, and other volatiles emit strongly. The data from that observation, released on August 25th, confirmed active outgassing of carbon dioxide, lots of it, along with carbon monoxide, water ice, and carbonyl sulfide. What was unusual, though not unprecedented, was the ratio. 3I Atlas was producing about 8 times more carbon dioxide than water vapor. Most solar system comets show the opposite pattern. Water dominates with CO2 as a secondary component. This high CO2 to water ratio suggested that 3I Atlas formed in an extremely cold environment far from its parent star, where CO2 could remain frozen while water was less abundant. This made perfect sense for an interstellar traveler. It had likely originated in the outer reaches of another stellar system, perhaps ejected by gravitational interactions with giant planets, then spent millions or billions of years drifting through the near absolute zero temperature of interstellar space. In that frozen state, it would preserve whatever chemistry existed at its birth. Throughout August and September, Atlas brightened steadily as it approached the Sun. This is normal behavior for comets closer to the heat source. More ice sublimates, more gas and dust fill the coma, reflecting more sunlight back toward observers. The comet moved southward through the constellations, crossing from Ophiuchus into Scorpius, then Libra, becoming easier to observe from southern hemisphere locations. By early October, it had reached magnitude 12, still too faint for naked eye visibility, requiring at least an 8-inch telescope under dark skies, but bright enough for serious amateur astronomers to photograph and track. The online astronomy community buzzed with images and observations, contributing data to professional researchers who were coordinating a comprehensive observing campaign. The trajectory calculations were refined with each passing week. As more observations accumulated, orbital dynamicists could plot 3I Atlas's path with increasing precision. The numbers confirmed something remarkable: this object would pass very close to Mars on October 3rd, coming within about 30 million kilometers of the red planet. That's closer than Mars ever gets to Earth. Close enough that spacecraft orbiting Mars would have an unprecedented opportunity to observe an interstellar visitor. And then came the detail that would spark months of debate and speculation: the perihelion date. Based on its velocity and trajectory, 3I Atlas would reach its closest approach to the Sun perihelion on October 29, 2025, at a distance of 1.356 astronomical units. That's 203 million kilometers, comfortably between the orbits of Earth and Mars, no danger whatsoever to our planet. But here's what made that date significant: it coincided almost perfectly with solar conjunction as viewed from Earth. On October 21st, 8 days before perihelion, 3I Atlas would pass directly behind the Sun from our perspective. The geometry of this alignment meant that during the most critical phase of the comet's passage, when solar heating would peak, when any fragmentation or unusual activity would most likely occur, Earth-based telescopes would be completely blind. The Sun's glare would wash out any attempt to observe the comet directly. Only spacecraft positioned elsewhere in the solar system, away from the Earth-Sun line, would have clear views. This alignment happens. It's geometry, not conspiracy. Objects on hyperbolic trajectories can cross behind the Sun as easily as they can cross in front of it. The timing is determined by orbital mechanics, by the comet's velocity and the angle at which it entered our solar system. Nothing mysterious about the physics, but the coincidence still felt uncanny. The universe arranging itself so that the most important observation window would be closed to most of humanity's telescopes. As October approached and the comet dipped lower toward the southern horizon, slipping toward that solar conjunction, observers captured their final clear images before the blackout. The coma remained active, the tail stretched behind the nucleus, and the spectroscopic signatures continued showing that unusual chemical mix. Then, on October 3rd, 3I Atlas passed within 28 million kilometers of Mars, and the spacecraft orbiting the red planet captured something that would fuel speculation for months to come. Let's talk about what made 3I Atlas genuinely unusual, because there's a difference between weird and unprecedented. Every comet is unique in some way. They're individuals, each carrying the chemical fingerprint of their formation environment, shaped by billions of years of exposure to cosmic radiation and sporadic warming from distant stellar encounters. Finding one that behaves strangely shouldn't immediately trigger appeals to extraordinary explanations. But 3I Atlas accumulated a collection of oddities that, taken together, pushed it beyond typical, interesting comet territory into something that demanded serious scientific attention and legitimate debate. The first anomaly was its trajectory alignment with the ecliptic plane. The ecliptic is that flat disk where Earth and the other planets orbit around the Sun. It's the plane of the solar system defined by the original protoplanetary disk, from which everything formed 4.6 billion years ago. Most objects gravitationally bound to the Sun stay close to this plane because that's where they were born. But interstellar objects shouldn't care about our ecliptic. They arrive from random directions in three-dimensional space, coming from wherever they happen to be ejected in whatever star system created them. Their trajectories should be isotropically distributed equally likely from any direction, showing no preference for our ecliptic plane. 3I Atlas, however, was traveling within 5 degrees of the ecliptic. It was almost coplanar with the planets, as if it had specifically targeted that orientation. Statistical analysis suggested this had only about a 0.2% probability for a truly random interstellar arrival, not impossible but definitely noteworthy. Critics quickly pointed out a selection bias. Survey telescopes like Atlas and Pan-STARRS focus their searches along the ecliptic because that's where near-Earth asteroids and potential impactors would be found. An interstellar object arriving from high inclination might never be detected because we're not looking as intensively in those directions. So perhaps 3I Atlas's ecliptic alignment simply reflected where we were looking hardest, not anything special about the object itself. Fair point. Selection effects are real and important in astronomy, but it didn't fully resolve the question because other interstellar objects hadn't shown this pattern. Oumuamua came in at a much steeper angle, so did 2I Borisov. The argument of observational bias couldn't completely explain away the alignment. The second anomaly appeared in late July, the anti-tail phenomenon. Most comets develop tails pointing away from the sun, driven by solar wind and radiation pressure pushing gas and dust outward. That's basic physics. Sunlight carries momentum, and when it reflects off or gets absorbed by dust particles, it imparts force in the direction away from the light source. But observers captured images of 3I Atlas showing a jet of material pointing toward the sun, not away from it. This wasn't a perspective effect or optical illusion from viewing angle. Careful analysis of multiple observations from different locations confirmed that material was genuinely moving sunward against the radiation pressure. This isn't unheard of. Some comets exhibit anti-tail features due to complex rotational dynamics and asymmetric outgassing. If your comet is spinning and has active vents on specific locations, the rocket effect from gas jetting out can create thrust in unexpected directions, including toward the sun under certain geometric configurations. Comet McNaught in 2007 showed similar features, but for 3I Atlas, the anti-tail was stronger and more persistent than typical cases. It lasted through July and August, then disappeared in September. This pattern sustained unusual activity, followed by cessation, struck some researchers as suggestive of something beyond random outgassing variations. The third anomaly was sheer size and mass. Based on brightness measurements and reasonable assumptions about surface reflectivity, 3I Atlas appeared to be at least 5 kilometers in diameter, possibly as large as 20 kilometers. Depending on exactly how much light its surface reflects versus absorbs. This made it roughly 1,000,000 times more massive than Oumuamua and 1,000 times more massive than 2I Borisov. That's an enormous difference. Statistically, larger objects are rarer. For every kilometer-sized asteroid in the asteroid belt, there are thousands of 100-meter objects and millions of 10-meter rocks. The size distribution follows a power law: abundance drops rapidly as size increases. Applying this same logic to interstellar objects, we should see many small visitors before we see large ones. The fact that our first 3 detections included 2 relatively small objects and 1 massive outlier seemed backwards statistically improbable. Unless, of course, our sample size was too small to mean anything. 3 detections isn't enough data to characterize a population. We might simply be seeing statistical noise, the random variation expected when sampling from any distribution with limited data points. The fourth anomaly was chemical, the nickel signature. Spectroscopic observations by the Very Large Telescope in Chile on August 21st detected emission lines characteristic of nickel vapor in the coma. This wasn't completely unprecedented. Some solar system comets do show traces of nickel, but the abundance was unusually high and came with an odd detail: very little iron. Nickel and iron are cosmic twins. They form together in the cores of massive stars and get blasted into space together when those stars explode as supernovae. Every meteorite we've studied, every asteroid we've sampled, shows nickel and iron together in roughly equal proportions. That's just how cosmic chemistry works. 3I Atlas showed abundant nickel but negligible iron. This mismatch suggested either exotic formation conditions we've never encountered or some kind of chemical fractionation process that separated these normally inseparable elements. Natural explanations exist. Perhaps the parent star that created 3I Atlas had unusual composition. Perhaps the comet formed in a region where some weird stellar nucleosynthesis produced nickel-rich, iron-poor material. Perhaps billions of years of space weathering and cosmic ray bombardment preferentially depleted iron from the surface while preserving nickel. All of these are possible, but they're also special pleading, inventing uncommon scenarios to explain uncommon observations. Sometimes the simplest explanation is that we're seeing something genuinely unusual that doesn't fit neatly into our existing frameworks. The fifth anomaly involved that CO2 to water ratio. 8 times more carbon dioxide than water isn't impossible for a comet formed in extremely cold conditions, but it's rare. It suggests formation very far from the parent star in conditions where CO2 could dominate. This told us something about 3I Atlas's origin. It came from a cold environment, perhaps the outer reaches of another stellar system. The sixth anomaly was perihelion survival. When 3I Atlas passed closest to the Sun on October 29th, it was being heated by about 770 watts per square meter of solar radiation. That's substantial thermal input, enough to sublimate massive amounts of ice, enough to potentially fracture a weakly bound comet into fragments that would then break down further under their own outgassing pressure. Many comets don't survive perihelion intact. Sun-grazing comets regularly disintegrate into clouds of debris. Even comets at more modest distances sometimes split apart. Comet Linear in 2000, Comet Atlas C 2019, Y4 in 2020, both fragmenting under thermal stress. 3I Atlas survived. It emerged from perihelion intact, continuing on its trajectory without obvious fragmentation or catastrophic brightening from a breakup event. This suggested a more cohesive structure than typical dirty snowball SAU comets, perhaps higher density, perhaps different composition, perhaps simply good luck with internal structure that happened to be strong enough to hold together. The seventh anomaly was what observers didn't see. Despite all that solar heating at perihelion, 3I Atlas didn't brighten as much as models predicted. Comets typically surge in brightness as they approach the Sun, outgassing increasing exponentially with decreasing distance. The standard models, based on decades of comet observations, predicted 3I Atlas should hit magnitude 11.5 at perihelion. It actually reached magnitude 9 to 10, according to space-based observations, brighter than predicted, but not from increased gas and dust production. Instead, the brightness seemed to come from reflected sunlight off the nucleus itself, as if the object was more reflective or larger than initially estimated rather than producing more outgassing activity. This pattern surviving perihelion without fragmenting brightening from reflection rather than sublimation suggested something with properties unlike typical comets, more like a solid body with relatively low volatile content. The eighth and final anomaly was the radio observation. NASA's Parker Solar Probe, positioned close to the Sun during the perihelion passage, detected radio emissions near the hydrogen line frequency of 1.42 gigahertz. This is the wavelength that neutral hydrogen atoms naturally emit, and it's also the frequency that SETI researchers monitor because any technological civilization would recognize its significance. The Parker data showed brief bursts of radio emission coming from the direction of 3I Atlas. Natural radio emission from comets isn't impossible. Excited atoms in the coma can produce massive effects under the right conditions. But the timing and characteristics of these emissions were unusual enough to warrant mention in the scientific literature. Taken individually, each of these 8 anomalies could be explained through natural processes, often requiring unusual conditions, but nothing that violated known physics. The ecliptic alignment could be selection bias. The anti-tail could be asymmetric outgassing. The large size could be statistical fluke. The nickel signature could be exotic stellar chemistry. The CO2 ratio could be cold formation. The perihelion survival could be structural luck. The brightness pattern could be high albedo. The radio emissions could be natural macers. But taken collectively, these 8 anomalies painted a picture that bothered some scientists. It was the combination, the way these unusual features clustered in a single object, that pushed probability toward uncomfortable territory. Harvard astrophysicist Avi Loeb, who had gained both fame and criticism for his suggestions that Oumuamua might be artificial, assigned 3I Atlas a ranking of 4 on his Loeb scale, a 0 to 10 spectrum, where 0 means definitively natural and 10 means definitively technological. A ranking of 4 indicated unusual but probably natural, worth taking seriously the possibility of artificial origin. Mainstream astronomers quickly pushed back. The overwhelming consensus remained that 3I Atlas was a comet, albeit an unusual one that exhibited rare but natural phenomena. Dr. Daryl Seligman, who led several studies on the object, emphasized that numerous telescopic observations demonstrate classical signatures of cometary activity. The outgassing, the coma, the tail, the spectroscopic signatures all pointed toward a natural icy body, responding to solar heating exactly as comet physics predicts. Dr. Chris Lintott and other astronomers expressed disappointment that speculation about artificial origin distracted from the genuine scientific value of studying this remarkable interstellar visitor. They worried that public attention on alien spacecraft hypotheses undermined serious research and damaged astronomy's credibility. The debate wasn't about whether 3I Atlas was interesting. Everyone agreed it was fascinating. The debate was about how we interpret unusual data. Do we exhaust natural explanations first, however unlikely? Or do we seriously entertain extraordinary hypotheses when conventional explanations require stacking multiple low-probability scenarios? As October 29th approached and the comet slipped behind the sun, from Earth's perspective, that debate intensified. Because during those hours when we couldn't observe directly, something would happen at perihelion that might provide more data or might deepen the mystery further. At 11:47 Universal Time on October 29, 2025, 3I Atlas reached perihelion. It crossed that mathematical point in space where its distance from the Sun was minimized. 203 million kilometers, a number calculated and refined through months of observations, predictable down to the minute based on gravitational physics that has proven reliable since Newton. For context, Mercury orbits at an average distance of 58 million kilometers. Earth sits 150 million kilometers out. Mars averages 228 million. So 3I Atlas's perihelion lay comfortably between Earth and Mars, nowhere near close enough to pose any danger, but certainly close enough to experience significant solar heating. At that distance, each square meter of 3I Atlas's surface received approximately 770 watts of solar radiation, about half what Earth receives, enough to warm frozen volatiles, considerably enough to drive active sublimation of carbon dioxide and water ice from the subsurface layers where solar heat could penetrate. This was the moment of maximum stress, maximum activity. The point where any comet would reveal its structural integrity. Would it hold together or fragment? Would it brighten dramatically from enhanced outgassing? Would it develop new jets or tails from the sudden heating we couldn't watch? Not from Earth, anyway. The geometry was unforgiving. 3I Atlas had reached the solar conjunction on October 21st, passing behind the Sun as viewed from our planet. By the time perihelion arrived 8 days later, the comet was positioned roughly 13 degrees from the Sun's edge, as seen from Earth, technically visible if you could block the Sun's overwhelming brightness, but practically impossible from ground-based telescopes. The Sun is brutally bright, outputting more light per second than we can easily comprehend. Point a telescope at anything within about 20 degrees of the solar limb, and scattered light floods your detectors, washing out everything else. It's like trying to spot a candle flame sitting next to a searchlight. The physics simply doesn't cooperate. So Earth-based observatories went blind during the critical window. Major facilities like the Very Large Telescope Keck Gemini all lost direct line of sight. Professional astronomers had to rely on space-based assets positioned elsewhere in the solar system. Several spacecraft rose to the occasion. NOAA's GOES-19 weather satellite, equipped with coronagraphs designed to study the sun's corona by blocking the bright disk, managed to capture images of 3I Atlas between October 18th and 24th as the comet crossed through its field of view. The images showed the comet as a faint smudge magnitude, roughly 11, moving against the background stars. The Punch mission polarimeter to unify the corona and heliosphere. A constellation of 4 satellites launched to study solar wind also caught glimpses. Punch's instruments track material flowing outward from the sun, and 3I Atlas briefly appeared in their wide-field imagers as it transited near the solar disk. The Solar and Heliospheric Observatory SOHO, that venerable spacecraft that's been watching the sun since 1995, detected the comet in its LASCO coronagraph images. SOHO has actually discovered thousands of comets over its lifetime, mostly sun grazers, that dive close to the solar surface. 3I Atlas was much farther out, but still within SOHO's detection range. And NASA's Parker Solar Probe, the mission designed to dive closer to the sun than any previous spacecraft, was well positioned to make measurements. Parker wasn't close enough to image 3I Atlas directly, but its instruments could detect radio emissions, plasma interactions, and magnetic field disturbances that might reveal activity from the comet. The initial data started arriving within hours of perihelion, transmitted back to ground stations and processed by science teams eager to see what had happened during the blackout. The first surprise was brightness. Space-based photometry showed 3I Atlas had brightened to approximately magnitude 9 to 10 at perihelion, significantly brighter than the predicted magnitude 11.5 based on pre-perihelion observations and standard cometary brightness models. That's a substantial difference. Each magnitude represents a factor of 2.5 in brightness, so the comet was roughly 3 to 4 times brighter than expected. This could mean several things, none of them particularly mysterious on their own. Perhaps the initial size estimates were wrong, and the nucleus was larger than calculated, reflecting more sunlight. Perhaps the surface albedo was higher than assumed. Perhaps outgassing ramped up more dramatically than predicted. Or perhaps the brightness increase was exactly what you'd expect from a comet getting closer to intense heat. More sublimation, more dust in the coma, more surface area reflecting sunlight. The second surprise involved color. Dr. Qicheng Zhang at Lowell Observatory and Carl Battams at the Naval Research Laboratory analyzed the space-based imagery and noticed something odd. 3I Atlas appeared bluer than expected. Comets usually show reddish colors from organic tholins and dust particles that preferentially scatter and absorb shorter blue wavelengths while reflecting longer red wavelengths. But 3I Atlas's spectral measurements showed it was reflecting light with a color temperature closer to solar, slightly bluer than the sun itself, which shouldn't happen if the reflected light was passing through a dusty coma. The researchers noted this was very surprising and suggested it might indicate unusual dust properties or gas emissions producing blue-shifted spectral lines. Natural explanations existed. Perhaps the dust grains were smaller than typical comet dust, which would scatter blue light more efficiently. Perhaps carbon monoxide and carbon dioxide emissions, which can produce blue-shifted spectral features, were dominating the light signature. Perhaps the observations were catching scattered sunlight from a relatively dust-free region, while the bulk of the coma was hidden behind the solar disk. The third detail from perihelion involved swift observatory measurements. NASA's Neil Gehrels Swift Observatory, equipped with ultraviolet and optical telescopes, captured observations in late July and August, plus follow-up data after perihelion. The scientists detected hydroxyl radicals OH molecules in the coma, which is a chemical signature of water vapor breaking down under ultraviolet radiation. This was good news for the "it's just a comet" hypothesis. Water detection confirmed that 3I Atlas possessed the icy volatiles expected in cometary bodies. The OH emissions followed patterns consistent with natural solar heating, driving sublimation from the nucleus. But the OH detection raised a question too. If water was present and active, why had earlier observations shown such a high CO2 to water ratio? The answer likely involved observational geometry and distance. Water sublimates less readily than CO2 at large solar distances. As 3I Atlas got closer and warmer water became more prominent, normalizing the ratio toward typical cometary values. ESA's Jupiter Icy Moons Explorer JUICE passed within 64 million kilometers of 3I Atlas on November 4th, about 6 days after perihelion. JUICE was on its way to Jupiter, not designed for comet observations, but mission controllers temporarily redirected its instruments to capture whatever data they could from this unexpected opportunity. JUICE's instruments included high-resolution cameras, spectrometers, capable of analyzing coma composition, and radiation detectors that could measure particle environments around the comet. The spacecraft spent 42 minutes observing 3I Atlas, collecting photometry and spectroscopic data. The preliminary results, transmitted back to Earth and processed by the science team in Darmstadt, Germany, confirmed the earlier space-based observations. 3I Atlas was brighter than predicted, still maintaining an active coma, still outgassing as it receded from perihelion. One detail caught attention: the brightness distribution around the nucleus wasn't perfectly symmetric. Natural comets often show asymmetric comas. Jets from active regions on the rotating nucleus create clumpy, uneven distributions of gas and dust, but JUICE's images seem to show multiple distinct bright regions around the central body, possibly 7 separate enhanced brightness zones. This is where observation blurs into interpretation. Were these genuine separate structures or artifacts of viewing geometry? Were they individual jets from active vents on a rotating nucleus, which would be completely normal? Or were they something else? The science team emphasized caution. JUICE's cameras weren't optimized for this observation. The comet was at the edge of the instrument's sensitivity range. Background noise and processing artifacts could easily create apparent structures that didn't physically exist. More data would be needed to confirm whether those brightness variations represented anything unusual, but the observations sparked discussion. If there were multiple discrete bright spots, and if they showed independent motion relative to the main nucleus, that would suggest material had separated from the comet fragmentation perhaps, or ejected chunks of ice and rock following ballistic trajectories after being blown off by outgassing jets. Comets fragment. This is well-documented behavior. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before impacting Jupiter in 1994. Comet Linear disintegrated in 2000. Comet Atlas, different object, coincidentally same survey name, fell apart in 2020. The mechanisms involve thermal stress, tidal forces, rotational stress, or structural weaknesses giving way under the violence of active outgassing. If 3I Atlas had shed fragments at perihelion, that would be completely natural behavior, requiring no exotic explanations. The only questions would be how many fragments, how large, and where were they headed? Parker Solar Probe's radio data added another layer of intrigue. The spacecraft detected brief bursts of radio emission near 1.42 gigahertz, the famous hydrogen line frequency. These emissions appeared to come from the general direction of 3I Atlas, though precise localization was difficult given the instrument's field of view and the comet's position. Comets can produce radio emissions through natural matter effects population inversions in excited atomic states, creating coherent amplification of specific wavelengths. Hydroxyl masers at 18 centimeters wavelength are well known from comets. Hydrogen line emission isn't common, but isn't impossible either under the right conditions of density, temperature, and excitation. The timing was interesting, though. The bursts occurred during the perihelion window, coinciding with maximum solar heating and presumably maximum cometary activity. Cause and effect. Or coincidence. These were the facts, the actual documented observations from spacecraft and telescopes that witnessed what happened on October 29th. 3I Atlas reached perihelion, survived intact. Brightened more than expected, showed unusual color properties, confirmed water emissions, possibly shed some fragments, and produced radio emissions near a significant frequency. Everything observed was explicable through natural comet physics, though some details pushed into unusual territory requiring less common explanations. Nothing violated known physics. Nothing demanded invoking artificial origin. But the combination of these observations, added to the earlier anomalies from July and August, kept the debate simmering. As 3I Atlas emerged from behind the Sun in early November, visible again to ground-based telescopes, astronomers pointed every available instrument at it, hoping the next phase of observations would resolve lingering questions. Let's take a careful walk through the territory where observation meets interpretation, where real data encounters human pattern recognition, and where the line between signal and noise becomes philosophically complicated. The facts are, these Parker Solar Probe detected radio emissions near 1.42 gigahertz from the region of sky containing 3I Atlas. These emissions were brief, lasting seconds to tens of seconds. They occurred during the perihelion window when the comet was closest to the Sun. The hydrogen line frequency, 1.42045 gigahertz to be precise, holds special significance. This is the wavelength that neutral hydrogen atoms emit when their electron transitions from one quantum state to another from the triplet state where electron and proton spins are aligned to the singlet state where spins are opposed. The energy difference corresponds to a photon at this exact frequency. Hydrogen is the most abundant element in the universe, comprising about 75% of normal matter by mass. Any technological civilization would know about hydrogen's emission line because it's fundamental physics impossible to miss if you're studying the cosmos. For this reason, SETI researchers have monitored 42 GHz since the 1960s, hoping that alien transmissions might beacon at this universal frequency that any scientifically literate species would recognize. The WOW signal, detected by Ohio State's Big Ear telescope on August 15, 1977, was centered at this frequency. It was so strong, so narrowband, so unexpected that astronomer Jerry Emmons scribbled "Wow" on the computer printout the next day when reviewing the data. Despite decades of follow-up observations, the signal was never detected again, and its source remains unexplained. So when Parker detected emissions at 1.42 GHz from 3I Atlas's direction, it inevitably triggered associations. Same frequency, same cosmic significance, same tantalizing possibility of deliberate signaling. But here, we must engage our critical thinking faculties. Correlation doesn't imply causation, and pattern recognition is a feature of human cognition that can produce false positives. First, let's understand what comets actually do in terms of radio emission. Cometary comas contain excited atoms and molecules, gas that's been heated, ionized or energetically excited by solar radiation, solar wind particles, and UV photons. Under the right conditions of density, temperature, and pumping mechanisms, these excited species can produce maser emission coherent radio waves amplified through stimulated emission. Hydroxyl masers at 18 centimeters on 1.67 GHz are well documented from comets. The OH radical produced when water molecules break down under UV radiation can create population inversions that lead to maser action. Several comets have been detected showing OH masser emissions strong enough to observe from Earth. Could hydrogen do the same thing? Theoretically, yes. Hydrogen is abundant in cometary comas. If conditions were right, specific densities, temperatures, and excitation mechanisms, you could imagine hydrogen transitions, producing enhanced emission at the 21 centimeter line. The challenge is that natural masers typically require very specific conditions that aren't commonly met. They're somewhat rare phenomena, even for OH, which is more prone to maser action than hydrogen. Detecting hydrogen line emission from a comet would be unusual but not impossible. Second, let's consider observational challenges. Parker's solar probe wasn't designed for radio astronomy. Its radio instruments are meant to detect plasma waves and solar radio bursts, not to act as precision spectrometers capable of resolving narrow spectral features. The frequency, resolution, and localization capabilities were limited. When Parker detected emissions near 1.42 GHz from the direction of 3I Atlas, those qualifiers matter. How close to 1? 42 GHz, within megahertz, within kilohertz. And how precisely was the direction determined, within degrees, within arc minutes? Without access to the full technical data, which likely remains in preliminary analysis, we can't evaluate these details. But they're crucial for determining whether the emissions genuinely came from the comet versus from some other source, solar radio burst, terrestrial interference, instrumental artifact that happened to appear in the same general sky region at the same general time. Third, let's address the elephant in the room. Pattern recognition bias. Humans evolved to find patterns because pattern recognition confers survival advantages. Our ancestors who notice patterns, predator tracks, weather signs, fruit ripening cycles survive better than those who didn't. This cognitive tendency, combined with our capacity for imagination, means we're exquisitely good at finding patterns even in random data. Play white noise long enough and you'll hear voices. Stare at static and you'll see faces. Show people random data with no embedded pattern, and a certain percentage will confidently identify structures that don't exist. This isn't deception or stupidity. It's normal human cognition doing what evolution designed it to do. Some observers claimed to detect patterns in the Parker radio data timing intervals that followed mathematical sequences as structured variations, suggesting encoded information. These claims spread through social media and were discussed in various online forums. But here's the critical question. Are those patterns actually in the data, or are they artifacts of the human brain's pattern-finding algorithms operating on noisy signals? Dr. Rachel Kim at the SETI Institute reviewed available data and noted that extracting meaningful structure from signals requires careful statistical analysis to rule out chance patterns. Without rigorous signal processing and probability calculations, apparent patterns could easily be coincidental. Consider if you have a signal with random variations in strength and timing, and you try enough different pattern matching schemes, eventually one of them will produce apparent correlation just by chance. This is the multiple comparisons problem in statistics. The more tests you run, the more likely you'll get false positives. Let's run a thought experiment. Imagine you're listening to cosmic radio static and you happen to catch a burst at 1.42 GHz, lasting 3 seconds, then silence for 5 seconds, then a burst for 8 seconds, then silence for 13 seconds. That's 3, 5, 8, 13. The Fibonacci sequence where each number is the sum of the previous two. Extraordinary. Surely this can't be random. The Fibonacci sequence appears everywhere in nature. Flower petals, spiral galaxies, breeding patterns, but finding it in radio emissions from a comet would suggest deliberate mathematical encoding. Except with how many different mathematical sequences might you compare the data, primes powers of two triangular numbers, factorial, Catalan numbers, pi's digits? If you test dozens of sequences against random noise, eventually one will match just by probability. This is why rigorous SETI protocols require not just pattern detection, but replication. The signal must be detected independently by multiple observatories. It must be seen repeatedly, not just once. And the pattern must be strong enough that the probability of chance occurrence falls below stringent thresholds, typically 1 in a million or better. The Parker observations don't meet those criteria. They were single detections, not replicated. The patterns, if they exist at all, haven't been confirmed by independent analysis. The probability calculations haven't been published in peer-reviewed literature. This doesn't mean the observations are worthless. They're interesting data points worth investigating further, but they don't constitute evidence of deliberate signaling without additional confirmation. Fourth, we should consider natural explanations for structured emissions. Even if the Parker data showed genuinely periodic variations or mathematical patterns, natural processes can produce structure. Rotating neutron stars, pulsars produce remarkably precise periodic radio pulses so regular they were initially called LGM, little green men, by the astronomers who discovered them in 1967. But they're not artificial. They're natural phenomena, neutron stars spinning at incredible speeds, with magnetic fields channeling radiation into beams that sweep across our line of sight like cosmic lighthouses. Maser emission can show variability driven by rotation precession or other periodic physical processes. If a comet is rotating with active jets that produce enhanced emission at certain orientations, you'd expect periodic variations as the jet rotates in and out of view. Could those variations happen to match a mathematical sequence? Perhaps. The cosmos is vast and full of phenomena. With enough observations of enough objects, eventually you'll find examples that match any sequence you care to name, simply because of the combinatorial explosion of possibilities. None of this is to say there's definitely nothing interesting in the radio data. The point is that extraordinary claims require extraordinary evidence, and preliminary, unconfirmed, single observation data don't meet that threshold. What would count as compelling evidence? Multiple independent detections from different instruments, emissions that couldn't be explained by any known natural process, patterns that were not just structured, but specifically encoded information like the Arecibo message, which deliberately organized binary data into a rectangular array that would be recognizable as artificial to anyone decoding it. Narrow band emission that varied in frequency in ways inconsistent with natural Doppler shifts, polarization characteristics indicating artificial generation, repeated transmissions that changed over time in response to detections suggesting interactive communication. None of these have been documented for 3i Atlas. What we have are intriguing hints, tantalizing coincidences and observations that push at the boundaries of normal cometary behavior, without definitively crossing those boundaries into impossible territory. As we contemplate these signals in the quiet hours before sleep, perhaps the most honest conclusion is this: we detected something unusual that warrants further investigation, but we shouldn't mistake our curiosity and hope for actual evidence. The universe is under no obligation to provide us with clear answers on our preferred timeline. Sometimes the most scientifically rigorous response is, "We don't know yet, let's keep watching." Now we enter territory where physics meets speculation, where real orbital mechanics suggest possibilities that stretch into science fiction without quite becoming impossible. This is thought experiment territory, labeled clearly as such, but grounded in genuine engineering principles. The Oberth effect is named after Hermann Oberth, one of the founding fathers of rocketry, who understood that the efficiency of spacecraft maneuvers depends critically on when and where you burn your engines. The principle is straightforward but counterintuitive. The kinetic energy gain from a propulsive burn is maximized when you're moving fastest. Here's why. Kinetic energy scales with the square of velocity e, 1/2. When you add velocity through propulsion, you're not just adding that velocity. You're also increasing the kinetic energy by an amount that depends on your current speed. If you're already moving fast and you add more speed, the energy gain is larger than if you add the same velocity change when moving slowly. For spacecraft operating in gravitational fields, this translates to a practical rule: burn your engines at perihelion, at the bottom of your trajectory, where orbital velocity peaks, and you'll achieve the maximum energy change per unit of propellant expended. This is how we send probes to the outer solar system. Cassini used a Venus-Earth-Jupiter gravity assist trajectory that involved multiple Oberth maneuvers at close approaches to planets, each one amplifying the energy gained through gravitational acceleration. Parker's solar probe uses Venus flybys to adjust its orbit timing, propulsive corrections, to coincide with high-speed perihelion passes for maximum efficiency. For 3I Atlas, perihelion represented the optimal moment for any trajectory change. At 203 million kilometers from the Sun, the comet was moving at its maximum heliocentric velocity, approximately 68 kilometers. If it possessed propulsion systems and wanted to alter course physics itself, mandated do it now. This is speculation. Let me emphasize that clearly. There is no confirmed evidence that 3I Atlas performed any maneuvers or deployed anything, but let's engage this thought experiment rigorously applying real physics to the what if scenario, because doing so illustrates what would be required and why it matters. Imagine you're an interstellar probe sent to survey a stellar system. You've been traveling for millions of years, conserving fuel following a carefully planned trajectory. You enter the system on a hyperbolic path designed to carry you past the inner planets for close observation. Your arrival is timed, perhaps deliberately, perhaps coincidentally, to pass closest to the Sun when your trajectory carries you behind it, as viewed from the primary inhabited planet. Why might this geometry be advantageous? Several reasons, none of them necessarily nefarious. If you wanted to deploy subprobes toward inner system targets, perihelion is when you do it. The gravitational well provides free energy. The high velocity allows efficient trajectory modification through relatively small velocity changes. Separating objects at perihelion gives them the widest range of potential destinations. The mechanics work like this: as you approach the Sun, you're falling into its gravitational well, accelerating, picking up speed that you didn't have to pay for with fuel. At perihelion, you momentarily possess enormous kinetic energy relative to the Sun. If you release objects with even modest velocity changes relative to your own motion, a few hundred meters per second achievable, with spring-loaded mechanisms or compressed gas ejection, those objects will follow significantly different trajectories as they climb back out of the gravity well. An object ejected forward, adding to your velocity, will gain more energy and follow a wider, faster trajectory. An object ejected backward, subtracting from your velocity, will fall into a tighter, slower orbit. An object ejected perpendicular to your motion will follow a path that carries it away from your trajectory plane. By carefully choosing ejection velocity and direction, you can target specific solar system bodies with precision, using the Sun's gravity to shape the resulting orbits. This is exactly how we deploy multiple spacecraft from single launch vehicles, by giving them slightly different velocity changes that propagate into significantly different final orbits. For 3I Atlas to deploy probes toward Earth, Venus, Mars, and other targets would require carefully choreographed releases at perihelion, each one ejected with specific velocity to achieve the desired trajectory. The energy requirements are substantial, but not impossible. Let's calculate. To redirect a probe from 3I Atlas's hyperbolic trajectory toward an Earth intercept course requires a velocity change delta V in the parlance of roughly 20 to 30 kilometers, depending on exact geometry and desired arrival time. Using the rocket equation, dv schaumskular visamadajuxor NUF, where v is exhaust velocity and m0 OMF is the mass ratio, For chemical rockets with exhaust velocities around 4 kilometers, achieving 25 kilometers delta V requires a mass ratio of about 501 impossible. Your rocket would be almost entirely fuel with negligible payload. But ion drives with exhaust velocities of 30 km/s reduce the mass ratio to about 2.3, one still challenging but achievable with advanced engineering. Nuclear thermal propulsion at 8-9 km exhaust velocity gives ratios around 20, one difficult but technically possible. Fusion propulsion, if achievable, would provide exhaust velocities measured in percentages of light speed. With 1% light speed exhaust velocity 3000 km/s, the mass ratio drops to barely above 1:1. You'd be mostly payload with just a small fuel fraction needed. This is where the speculation deepens. If 3I Atlas possessed such propulsion technology, if it carried probes with fusion drives or beyond, then the maneuvers we're imagining would be technically feasible. The physics allows it. The engineering would be far beyond human capability, but not beyond physical law. And here's where timing becomes suggestive. The perihelion occurred precisely when Earth couldn't observe directly. If you were designing a mission and wanted to perform maneuvers without being watched, you'd choose exactly this geometry. Or if you simply didn't care about being observed but were optimizing for efficiency, you'd do the same thing because physics demands it. Natural processes don't optimize. They don't plan. Comets don't care about observational geometry or fuel efficiency. They follow ballistic trajectories determined entirely by gravity and whatever outgassing forces randomly push them around. If 3I Atlas exhibited genuine trajectory changes inconsistent with gravitational and outgassing forces, if it changed course in ways requiring propulsion that would constitute strong evidence of artificial origin, nothing else would explain it. Did that happen? Based on publicly available tracking data, 3I Atlas has followed its predicted trajectory within observational uncertainties. No confirmed departures from gravitational orbit have been documented. The object behaves like a natural comet, should behave moving according to Newton's and Einstein's equations without adding extra terms for thrust. But outgassing forces can subtly alter trajectories. Comet orbits often show non-gravitational accelerations from rocket effects as gas jets off the surface. These effects are small meters per second velocity changes over months, but detectable with precise enough measurements. Could more substantial accelerations hide within the uncertainties of a rapidly moving hyperbolic visitor that's only observable for a few months? Possibly. Tracking an interstellar object is harder than tracking a periodic comet because you don't have decades of observations to refine the orbit. You're extrapolating from limited data and uncertainties compound. In the coming weeks of November and December 2025, as 3I Atlas continues outward past Earth's orbit, astronomers will refine their measurements. If the orbit continues matching gravitational predictions, that's strong evidence against propulsive maneuvers. If discrepancies emerge that can't be explained by outgassing, that opens new questions. For now, though, the Oberth maneuver scenario remains in the realm of informed speculation, physically possible, conceptually reasonable, if you grant the artificial hypothesis but not supported by conclusive evidence. It's a scenario worth considering because it illuminates what would be required and how we detect it, but it's not yet a conclusion we can draw from the data. As we think about this while drifting towards sleep, perhaps the most intriguing aspect isn't whether it happened, but that we can ask the question rigorously. We can run the calculations, predict the observations, design the tests. If artificial probes ever do arrive in our solar system, we'll recognize them because physics leaves signatures that can't be hidden. The universe plays by rules we're learning to read. And sometimes the most exciting discoveries begin with a speculation that leads to a prediction, that leads to an observation that changes everything we thought we knew. In the weeks following perihelion, as 3I Atlas emerged from behind the sun and astronomers resumed direct observations, something else emerged too. Viral claims spreading through social media, YouTube, and various forums that NASA had secretly activated a planetary defense protocol in response to anomalous behavior from the interstellar visitor. The claims varied in detail but shared common themes. 3I Atlas had performed unexpected maneuvers. Multiple probes had separated from the main body. NASA was tracking these objects on approach trajectories toward Earth. The International Asteroid Warning Network had been mobilized. Defense systems were being readied. A cover-up was underway. These narratives gained traction quickly amplified by algorithms that prioritize engagement over accuracy, shared by users who found the story compelling enough to spread without verification. Within days, videos discussing NASA's secret response to 3I Atlas were accumulating millions of views. Here's where we need to carefully disentangle fact from fiction, because the situation contains elements of truth that make the false elements more believable, the hallmark of effective misinformation. The facts. The International Asteroid Warning Network, IAWN, did issue a technical bulletin regarding 3I Atlas. The bulletin, released on October 21, 2025, announced a training campaign scheduled to run from November 27, 2025 through January 27, 2026. This campaign, labeled an astrometry training exercise, would focus on 3I Atlas as a target for improving measurement techniques. The bulletin emphasized that comets present unique challenges for accurate astrometric measurements and orbit predictions, due to their extended comas and morphological features that can systematically pull centroid measurements off their central brightness peak. The purpose of the exercise was explicitly stated to improve the astronomical community's ability to accurately measure comet positions and refine trajectory calculations. Participants would practice extracting precise astrometry from difficult targets, comparing methodologies, and calibrating their observational systems. This is completely routine. IAWN regularly conducts training exercises and campaigns to keep the global network of observers coordinated and skilled. These exercises use real objects as training targets because there's no better way to practice than with actual observations. What made this exercise notable was that 3I Atlas was the first interstellar object selected as an IAWN campaign target. Previous exercises focused on near-Earth asteroids or periodic comets. The choice of an interstellar visitor reflected both scientific interest in these rare objects and practical recognition that their hyperbolic trajectories present measurement challenges distinct from gravitationally bound solar system bodies. This was not an emergency response. It was not a defense protocol activation. It was a scheduled training exercise announced through normal channels published in the Minor Planet Electronic Circular, the standard mechanism for disseminating information about comets and asteroids to the astronomical community. But context collapsed online. The word warning in International Asteroid Warning Network triggered associations with emergency and threat. The timing announced during the perihelion blackout, when public curiosity about 3I Atlas was peaking, seemed suspicious to those predisposed toward conspiracy thinking. The fiction began layering onto these facts. Claims emerged that the IAWN bulletin was coded language, that the training exercise was cover for actual defense preparation. Older quotes from scientists discussing hypothetical interstellar threats were recontextualized to appear as if they referred specifically to 3I Atlas. Images of unrelated spacecraft were presented as evidence of defense systems being mobilized. One particularly persistent claim involved a supposed NASA planetary defense protocol that had been secretly activated. This claim likely originated from confusion between several real programs and fictional elements. NASA does have a Planetary Defense Coordination Office established in 2016, tasked with detecting, tracking, and characterizing potentially hazardous near-Earth objects. This office coordinates with international partners, supports research into deflection technologies, and would indeed be involved in coordinating response to any genuine impact threat. NASA has conducted asteroid deflection tests. The DART mission in 2022 successfully altered the orbit of asteroid Dimorphos by intentionally crashing a spacecraft into it. This demonstrated that kinetic impactor technology works for planetary defense, at least against small cooperative targets. But there is no secret protocol. NASA's planetary defense activities are public, transparent, and published. The Planetary Defense Coordination Office releases regular reports. Potentially hazardous objects are cataloged in publicly accessible databases. When objects warrant attention, that information is shared with the scientific community and press. For 3I Atlas specifically, NASA made clear and consistent statements. The object poses no threat to Earth. Its closest approach, occurring in mid-December 2025, would be at a distance of approximately 1.8 astronomical units, about 270 million kilometers, nearly twice the Earth-Sun distance. There was zero probability of impact. This wasn't reassuring platitudes. This was mathematical certainty. Orbital mechanics doesn't lie. With months of observations refining 3I Atlas's trajectory, astronomers could calculate its future path with high precision. The error bars on those calculations were tiny compared to the distance of closest approach. Unless the comet performed massive course changes orders of magnitude beyond anything observed, it would pass safely. But facts rarely defeat narratives once emotional investment takes hold. People who believed in the threat narrative found ways to discount official statements. NASA was covering up. Scientists were either fooled or complicit. The real data was being withheld. Coincidental events fed the narrative. The U.S. government experienced a brief shutdown starting October 1, 2025, due to congressional budget impasses. This shutdown affected NASA operations, causing temporary furloughs and reducing public communications. The timing was purely coincidental. Government shutdowns happen due to domestic political dysfunction, not cosmic visitors. But conspiracy theorists seized on it as evidence of information control. NASA went silent just as 3I Atlas approached perihelion. Clearly, they were hiding something. In reality, NASA's scientific operations continued during the shutdown. Deep space missions maintained functionality. Data collection proceeded. The shutdown primarily affected administrative functions and public outreach, not the actual science. Another source of confusion involved legitimate scientific speculation. Dr. Avi Loeb, Harvard astronomer and founder of the Galileo Project, had published several essays exploring the hypothetical possibility that 3I Atlas might be artificial. He carefully framed these as thought experiments, emphasizing if scenarios and acknowledging natural explanations as more likely. But nuance disappeared in viral transmission. Headlines condensed. Harvard scientist says we should consider the possibility, into Harvard scientist warns of alien probe. Speculation became assertion. Caution became certainty. Loeb himself addressed this distortion repeatedly, clarifying that his goal was to encourage rigorous scientific investigation of all possibilities, not to claim definitive knowledge of artificial origin. Science advances by entertaining hypotheses and testing them against evidence, not by dismissing uncomfortable ideas without examination. The most damaging fictional element involved supposed probes that had separated from 3I Atlas and were approaching Earth on deliberate intercept courses. This claim had zero basis in confirmed observations. Yes, comets can fragment. Yes, multiple objects could theoretically separate from a comet at perihelion, but tracking data showed no evidence of discrete objects following independent trajectories toward Earth. 3I Atlas remained a single target in professional observational databases. No additional designations were issued for companion objects. No alerts were released regarding incoming fragments. What observers did see were normal cometary features, jets, coma asymmetries, tail structures that varied as the comet rotated and outgassed. These features created brightness variations that might be misinterpreted as separate objects by casual observers or deliberately misrepresented by those seeking to promote alarming narratives. Amateur astronomers with appropriate equipment confirmed this through their own observations. 3I Atlas appeared as a single diffuse object with typical cometary morphology. No formation of discrete companions, no mysterious fragments tracking toward Earth. This is where media literacy becomes crucial. In an age where anyone can publish content and algorithms amplify engagement over accuracy, verification matters. Before accepting dramatic claims, we should ask, what's the primary source? Are multiple independent outlets reporting this? Do official agencies confirm it? What does the peer-reviewed scientific literature say? For 3I Atlas primary sources, NASA, ESA, professional astronomical organizations, consistently described it as an unusual but natural interstellar comet with no threat to Earth. Scientific papers published in journals documented the observations and analyses. No credible evidence supported the alarming claims circulating online. This doesn't mean we should never question official narratives or that institutions always tell the truth. Healthy skepticism has its place, but skepticism should be balanced, applied equally to sensational claims and official denials, weighted by evidence quality rather than entertainment value. As we contemplate this in the quiet evening hours, perhaps the lesson is this: truth often lacks drama. Real science involves uncertainty, gradual refinement of understanding, careful statements, hedged with caveats. Fiction offers certainty, clear villains and heroes, dramatic revelations that explain everything. Our brains prefer fiction's narrative structure because that's how we make sense of complex reality, through stories with beginning, middle, and end. But the universe doesn't owe us satisfying narratives. Sometimes the truth is, it's probably just a comet, though an interesting one, and we'll know more after collecting additional data. That's not clickbait, it's not viral, but it's honest. And in the long run, honesty serves us better than exciting lies that waste our attention and misdirect our curiosity away from genuine mysteries still waiting to be understood. Let's engage in rigorous speculation grounded firmly in physics and engineering about what would actually be required if, and this is clearly labeled as a thought experiment, 3I Atlas were artificial rather than natural. This exercise serves a purpose beyond idle wonder. By calculating the requirements for interstellar travel probe deployment and system operations, we define the boundaries between possible and impossible, between technology we might build someday and technology that violates physical law. First, consider the journey. 3I Atlas likely traveled for millions to billions of years across interstellar space before entering our solar system. The nearest star system, Alpha Centauri, sits 437 light-years away. At 68 kilometers s 3I Atlas's current velocity, that journey would take about 20,000 years. More distant origins mean longer travel times proportionally. For context, Voyager 1, humanity's most distant spacecraft, travels at 17 kilometers s and will take 40,000 years to pass, within 1.7 light-years of another star. We've never built anything designed to function for timescales longer than decades. The longest operating spacecraft, Voyagers 1 and 2, have survived nearly 50 years, with significant component degradation and careful management from ground controllers who upload patches and switch to backup systems when primary ones fail. An interstellar probe requires autonomy we can barely imagine. No ground control, no rescue missions, no spare parts shipments. Whatever launches must function across geological timescales. Surviving radiation exposure that accumulates to sterilizing levels, temperature swings from near absolute zero in interstellar space to solar perihelion heating, Micrometeorite impacts, cosmic ray bombardment, and the slow decay of radioactive materials used for power. Material science would need advances we're only beginning to conceptualize. Radiation-hardened electronics that don't degrade under cumulative dose. Self-healing structures that repair micrometeorite damage. Power systems that function for millions of years, likely nuclear fusion or matter-antimatter annihilation, since no conceivable battery or solar panel endures that long. The thermal challenge at perihelion deserves specific attention. At 203 million kilometers from the Sun, 3I Atlas received 770 watts per square meter. That's substantial heating enough to boil water hot enough to damage sensitive electronics without proper thermal management. Natural comets handle this through ablation ice sublimates carrying heat away. It's crude but effective. Artificial probes would need sophisticated thermal control radiators to dump heat insulation to protect internals, possibly active cooling systems. The engineering is conceivable but requires mass for heat exchangers, pipes, pumps, all adding to system complexity. Now consider propulsion. If 3I Atlas deployed probes at perihelion, and if those probes needed to redirect toward Earth from the parent object's hyperbolic escape trajectory, the energy requirements are staggering. The rocket equation governs all propulsion. dv kushagiladnitha vex ln m0 mf, your achievable velocity change. Delta V equals your exhaust velocity times the natural log of your initial to final mass ratio. This equation is tyrannical. It doesn't negotiate, doesn't care about your mission requirements, doesn't bend for clever engineering. To redirect from 3I Atlas's trajectory toward an Earth intercept course requires roughly 25 kilometers delta V, depending on exact geometry. Our best chemical rockets achieve exhaust velocities around 4.5 kilometers s. Plug into the rocket equation, you'd need a mass ratio of about 401. For every kilogram of probe, you need 400 kilograms of fuel and rocket. Completely impractical, ion drives improve things dramatically. With exhaust velocities of 30-50 kilometers from ionized xenon accelerated by electric fields, mass ratios drop to 2, 1, or 3:1. Achievable, but ion drives produce minuscule thrust fractions of a newton. Maneuvers take months or years of continuous operation. Nuclear thermal propulsion. Heating, hydrogen propellant with a reactor core delivers 8-9 kilometers exhaust velocity. Better than chemical, worse than ion. Mass ratios around 21 for 25 kilometers delta V. The technology exists conceptually. We've tested nuclear thermal engines but never flown them operationally. Fusion changes everything. If you can confine and control fusion reactions using the energy to heat propellant to extreme temperatures, exhaust velocities approach percentages of light speed. At 3,000 kilometers s 1% c, the rocket equation becomes almost irrelevant. Mass ratios barely exceed 1:1. But fusion is hard. We've been pursuing controlled fusion for 70 years with limited success. ITER, the International Fusion Experiment under construction in France, might achieve break-even energy output in the 2030s. Engineering fusion into a reliable, compact, spacecraft-suitable propulsion system represents centuries of development beyond break-even. If 3I Atlas used fusion, it's technology far beyond human capability. Not impossible physics allows it, but requiring advances we can't currently achieve. Beyond fusion lies antimatter. When matter and antimatter annihilate, they convert mass directly to energy with 100% efficiency, EI, MC2. The exhaust velocity from antimatter propulsion approaches light speed. You could achieve enormous delta V with tiny propellant fractions. The problem is production and storage. Antimatter doesn't exist naturally in useful quantities. We can produce it in particle accelerators, but at enormous energy cost and in microscopic amounts. CERN produces about 10 nanograms of antiprotons per year. A gram would take 100 million years at current production rates. And storage is nightmarish. Antimatter annihilates instantly upon touching normal matter. You need magnetic bottles or other exotic containment that prevents any contact while maintaining perfect reliability for millions of years. A single containment failure, and your fuel supply explosively converts to gamma rays. If Sky Atlas used antimatter propulsion, we're talking about technological sophistication so far beyond human civilization that comparison becomes meaningless. The navigation challenge deserves consideration too. Hitting Earth from millions of kilometers away while both you and target are moving at tens of kilometers per second requires precision that makes threading a needle look crude. Miss your trajectory by 1/1,000,000th of a degree, and you're off by thousands of kilometers at arrival. Natural objects don't hit targets with this precision. They follow ballistic paths, determined by gravity and initial conditions landing wherever physics takes them. Guided objects need real-time navigation sensors, tracking stars or planets for position-fixing computers, calculating trajectory corrections. Actuators executing those corrections with precisely timed thruster burns. This requires computational power robust enough to survive interstellar journey sensors, sensitive enough to detect navigation references across vast distances and propulsion systems responsive enough to make fine corrections. We can do this for missions within our solar system with ground support and decades of mission planning. Doing it autonomously across interstellar distances with no external assistance represents quantum leaps in reliability and autonomy. The power budget compounds all these challenges. Propulsion requires megawatts potentially. Communications across interstellar distances require kilowatts to overcome signal dispersion. Computing sensors, thermal control all need power continuously for millions of years. Solar panels work near stars but produce nothing in interstellar space. Radioisotope generators decay plutonium-238 currently. Our best option has a half-life of 88 years, meaning after 1,000,000 years, your power output has dropped by factors we can't even calculate meaningfully. Fusion provides power and propulsion in one package. Antimatter does likewise. Anything less runs into sustainability problems over the timescales required. Are we convinced yet that this is hard? That interstellar travel, autonomous navigation, million-year reliability, all demand capabilities far beyond current human technology. This doesn't make it impossible. Physics allows it. But the engineering represents centuries to millennia of advancement beyond our present state. Any civilization capable of 3I Atlas, if it were artificial, would be to us as we are to Stone Age hunter-gatherers, comparable in fundamental ways but separated by vast chasms of capability. This vast gap is actually reassuring for the natural comet hypothesis. If 3I Atlas were artificial, it would represent contact with beings so advanced that the gulf between us would be almost unbridgeable. That's not impossible, but it's a far heavier claim than "it's just a comet." Extraordinary claims require extraordinary evidence precisely because they invoke extraordinary scenarios. The technology required for interstellar probes is so far beyond human reach that positing its existence requires extraordinary justification. As we drift towards sleep, contemplating these calculations, perhaps we're left with awe at what physics permits and humility about what we've achieved. The universe allows wonders we can barely imagine governed by laws we're only beginning to understand. Whether 3I Atlas represents one of those wonders or simply a frozen relic from an alien star system, it reminds us how much remains unexplored in this vast cosmic darkness. Direction matters in the cosmos, though not in the way mystics or astrologers might claim. The direction from which an object arrives carries information about its origin, about the stellar neighborhoods it passed through, about the gravitational environment that shaped its trajectory across the light years. 3I Atlas entered our solar system from the direction of Sagittarius, that constellation of stars that to ancient Greek eyes resembled a centaur drawing a bow. The constellation itself is arbitrary, just our projection of pattern onto random stellar positions that happen to align from Earth's perspective. But what lies behind Sagittarius is anything but random. That direction, when you look past the foreground stars of the constellation, points toward the galactic center, the heart of our Milky Way galaxy, 26,000 light-years away, invisible in optical wavelengths because thick lanes of dust block visible light, sits Sagittarius A, the supermassive black hole around which our entire galaxy orbits. Sagittarius A masses approximately 4 million times what the Sun does. It's a gravitational monster warping space-time so severely that stars near it orbit at thousands of kilometers per second, their paths bent into tight ellipses by forces that would tear normal matter apart. Around that black hole in the galactic bulge, stars crowd together with separations measured in light days rather than light years. The stellar density there is millions of times higher than in our sparse galactic suburbs. Interactions are common. Close encounters, gravitational slingshots, systems disrupted and reformed by passing neighbors. It's a violent, dynamic region, nothing like the quiet neighborhood where our Sun peacefully orbits 26,000 light-years from the action. And it's from that general direction that 3I Atlas emerged after billions of years of travel. This doesn't mean 3I Atlas came from the galactic center specifically. Direction of arrival over interstellar distances doesn't point precisely at origin. The object's motion through space is affected by every gravitational field it passed through, every stellar encounter that perturbed its path, the galactic rotation itself that sweeps stars around the center like water circling a drain. Tracing 3I Atlas's trajectory backward, accounting for galactic motion and gravitational perturbations, the origin point remains stubbornly uncertain. It came from somewhere in the general direction of Sagittarius, from the inner galaxy perhaps, but pinpointing a specific star system is impossible over the distances and timescales involved. What we can calculate is probability. The galactic center occupies roughly 1% of the sky as viewed from Earth. If interstellar objects arrive from random directions, and they should, given that stars and planetary systems are distributed in 3 dimensions throughout the galaxy, then an object arriving from any specific 1% region has, 1% probability. Nothing extraordinary about that individually, but combine it with other observations and patterns start emerging. On August 15, 1977, the Big Ear radio telescope at Ohio State University detected a signal so strong and unusual that astronomer Jerry Eman, reviewing the computer printout the next day, wrote, "Wow," in the margin. The signal was narrowband centered at 1.420 gigahertz, the hydrogen line, and came from the direction of Sagittarius. Specifically, the signal originated near the Chi Sagittarii star group, close to the ecliptic plane. It lasted 72 seconds, the full time Big Ear's beam was pointed at that region of sky as Earth's rotation swept the telescope's view across the stars. Then silence. The signal was never detected again, despite decades of follow-up observations. The WOW signal remains unexplained. Natural explanations have been proposed: a comet releasing hydrogen, a satellite transmission, a military radar reflection, instrumental artifact. None fully satisfy. The signal's characteristics, narrowband, strong at the hydrogen line, match what SETI researchers expect from artificial transmissions, but also what certain natural masers could produce under rare conditions. Dr. Antonio Paris proposed in 2016 that Comet 266P Christensen, which happened to be transiting that region of sky in 1977, might have produced the signal through hydrogen clouds around the nucleus. Other researchers checked the orbital calculations and found the comet wasn't actually positioned correctly to explain the signal. The mystery persists. And now, 48 years later, we have 3I Atlas, another visitor from Sagittarius, another object showing unusual characteristics, another source of hydrogen line radio emissions. Is this correlation meaningful or coincidence? Let's calculate the odds rigorously. Sagittarius occupies about 1% of the sky. The probability of the WOW signal coming from that direction by chance, 1%. The probability of 3I Atlas arriving from that direction by chance, 1%. The probability of both occurring by chance, 1%, x 1%, or 0.01%, or 1 in 10,000. Not impossible. Improbable things happen constantly in a large universe. Flip a coin 14 times, and you've got 1 in 10,000 odds of getting all heads, yet someone somewhere has probably done it. But our calculation assumes independence, that the two events are unrelated. If they're correlated, if the wow signal was somehow connected to 3I Atlas, then the probabilities don't multiply independently. Instead, one might predict the other. Imagine a scenario purely speculative: an interstellar probe launches from some inter-galaxy civilization programmed to survey nearby stellar systems. As it enters each system, it sends a beacon ahead, a powerful narrowband radio transmission at the hydrogen line, the universal frequency any scientifically literate species would monitor. The beacon announces, "A visitor approaches. We mean no harm. Prepare to observe." 48 years later, the physical probe arrives. Earth has had 5 decades to develop better technology, improve our astronomy, prepare for contact. The timing seems generous, giving the locals time to get ready. This is wild speculation, but it's internally consistent and explains the correlation without violating physics. Advanced civilizations might reasonably announce their approach with radio beacons preceding physical arrival by decades. The problems with this scenario are numerous. Why send only one beacon? Why not repeat it? So detection is more likely. Why would the comet's arrival be timed to coincide so precisely with our modern observational capabilities? We detected 3I Atlas easily, but 50 years earlier, our survey telescopes wouldn't have spotted it as readily. And most problematically, if you're announcing arrival, why not communicate more clearly? Why one cryptic signal followed by decades of silence? It violates principles of robust communication design. You'd transmit repeatedly, in multiple formats, ensuring reception. The alternative explanation is simpler coincidence. The galaxy contains hundreds of billions of stars. The volume of space pointing toward the galactic center from our perspective includes countless stellar systems that could eject comets our direction. We've received 2 notable events from that region over 5 decades, the WOW signal and 3I Atlas, but we've also received millions of cosmic rays, numerous meteor impacts, regular solar emissions, all from random directions including Sagittarius. Pattern recognition is a powerful cognitive tool, but also a trap. We're evolved to detect agency, to find meaning, to connect dots into narratives. Show people random ink blots and they see faces, animals, significance where none exists. This tendency kept our ancestors alive better to mistake wind-rustling bushes for a predator and be wrong than miss the actual predator and become dinner. But in science, we must temper pattern recognition with statistical rigor. Before declaring a pattern meaningful, we calculate the probability of observing it by chance. We look for additional evidence that supports connection versus coincidence. We test predictions. If these events are related, what else should we observe? For the Sagittarius connection, what predictions arise? If there's a deliberate survey mission originating from the inner galaxy, we might expect additional visitors from similar directions spaced over time as different probes complete their journeys. We might expect communications attempts as each probe arrives, not just single bursts, but sustained efforts at contact. We might expect the objects themselves to show coordinated characteristics, similar technologies, similar approach strategies, similar timing. Instead, the WOW signal and 3I Atlas are separated by nearly half a century, with no intermediate events linking them. The galactic center itself, while fascinating, doesn't obviously favor technological civilization over other regions. Yes, stellar density is higher there, which might facilitate interstellar communication or resource sharing between nearby systems. But conditions are also more violent, high radiation, frequent supernovae, gravitational disruptions. life might find more stable environments farther from the core. Our own location in the galactic suburbs, in a quiet spiral arm where stars are spaced light years apart, might actually be advantageous for complex life. Stable orbits, low radiation background, infrequent catastrophic events. The rare Earth hypothesis suggests that conditions suitable for complex life are unusual, requiring multiple factors aligning just right. If that's true, the galactic center might be less likely to host technological civilizations than the calmer outer regions, which would make the Sagittarius direction less significant as an origin for contact attempts. As we ponder this connection in the evening, quiet, perhaps the most intellectually honest conclusion, is interesting coincidence worth noting, insufficient evidence to claim meaningful connection. The universe is vast and full of coincidences simply because vast universes generate every possible combination of events eventually. Sometimes a coincidence is just that random alignment of independent phenomena that our pattern-seeking minds weave into narrative. But we should keep watching Sagittarius. If additional anomalies emerge from that direction, if patterns strengthen with more data, then we revisit these questions with better evidence. Science progresses through patient accumulation of observations, not through premature conclusions based on limited data. For now, 3I Atlas remains a fascinating interstellar comet that happened to arrive from the same general sky region as an unexplained radio signal 48 years earlier. Suggestive yes, definitive no. And that uncertainty, that not knowing, is precisely what drives science forward into the darkness, seeking answers to questions we've only begun to formulate. As December approaches, and the year 2025 draws toward its close, 3I Atlas continues its outbound journey, receding from the Sun along a hyperbolic trajectory that will eventually carry it back into interstellar space, never to return to our stellar neighborhood. The orbital mechanics are straightforward, now refined by months of observations into precise predictions. The comet passed perihelion on October 29th at 1.356 AU from the Sun, 203 million kilometers. After that closest approach, it began climbing back out of the solar gravitational well, following the other branch of its hyperbolic path, gaining distance from the Sun with each passing day. On November 3, 2025, 3I Atlas passed within 0.65 AU of Venus, approximately 97 million kilometers. This was a geometric coincidence, two objects following different orbits that happened to bring them into relative proximity. Venus, orbiting in its nearly circular path around the Sun, was positioned just right for the comet's trajectory to carry it nearby. No interaction occurred. Venus's gravity, though substantial for a terrestrial planet, was far too weak at that distance to measurably alter 3I Atlas's trajectory. The gravitational influence drops with the square of distance, so at 97 million kilometers, Venus's pull was negligible compared to the Sun's dominant gravitational field. But the close approach did provide observation opportunities. NASA's Parker Solar Probe and ESA's Bepi-Colombo mission to Mercury, both operating in the inner solar system, were positioned to potentially observe the comet during the Venus passage. Whether they collected usable data hasn't been publicly announced, yet science returns from space missions often take months to process and analyze. Now in late November and early December, 3I Atlas is approaching its closest point to Earth. On December 19, 2025, the comet will pass at a distance of 1.80 AU, approximately 269 million kilometers, nearly twice the Earth-Sun distance. This is as close as 3I Atlas will ever get to our planet. The geometry of its hyperbolic trajectory combined with Earth's orbital position in late December brings the two objects to minimum separation at this date and time. After December 19th, the distance will only increase as both objects continue their respective journeys. There is zero risk to Earth. Let me emphasize that with complete confidence. At 269 million kilometers, separation 3I Atlas is farther from Earth than Mars is on average. There's no gravitational influence, no possibility of impact, no plausible scenario where it could pose danger. The comet will be observable from Earth during December with appropriate equipment. Magnitude predictions suggest it will brighten to around 11.5, too faint for naked eye or binoculars, but accessible to backyard telescopes with 8-inch or larger apertures under dark skies. For professional astronomers, December represents a golden opportunity. As 3I Atlas recedes from the Sun and climbs higher above the ecliptic plane, it emerges from the solar glare that obscured it during October and November. Ground-based telescopes in both hemispheres will have clear sight lines, enabling continuous observations that weren't possible during perihelion. The observation campaigns are comprehensive. NASA's Hubble Space Telescope is scheduled to observe 3I Atlas multiple times in December, capturing high-resolution images that will reveal details about the coma structure, nucleus size, and any changes in activity level as the comet moves away from peak solar heating. The James Webb Space Telescope will make additional infrared observations following up on its August spectroscopy to measure how the chemical composition changes with distance from the Sun. As temperatures drop, some volatiles will stop outgassing, allowing researchers to map the depletion sequence, which gases shut off first, which persist longest, revealing the temperature distribution and composition of the nucleus. Ground-based spectroscopy will continue tracking emission lines from molecules in the coma. Particular attention will focus on that nickel signature and the CO2-to-water ratio, monitoring whether these unusual characteristics persist or normalize as the comet recedes. After its December 19th Earth approach, 3I Atlas will continue outward, crossing Mars's orbital distance in January 2026, reaching Jupiter's orbital radius by March 16, 2026. The comet will pass within 0.36 AU of Jupiter, about 54 million kilometers, providing another opportunity for spacecraft observations. NASA's Juno mission orbiting Jupiter since 2016 could potentially observe 3I Atlas if mission planners choose to retask the spacecraft temporarily. Juno's instruments are optimized for studying Jupiter's atmosphere and magnetosphere, but they could collect data on an interstellar comet passing nearby. ESA's JUICE spacecraft, currently en route to Jupiter, will be positioned in the inner solar system during 3I Atlas's Jupiter pass. JUICE made that November 4th observation from 64 million kilometers. By March 2026, the spacecraft will be even better positioned for follow-up observations. After Jupiter, 3I Atlas will continue its exodus from the solar system. By late 2026, it will cross beyond Saturn's orbital distance, entering the outer solar system where sunlight dims and temperatures plummet. The coma will likely shut down entirely as remaining volatiles freeze solid, leaving just the bare nucleus, a dark, inert rock tumbling through the void. Over subsequent years and decades, 3I Atlas will traverse the Kuiper Belt, that region beyond Neptune where countless icy bodies orbit in the frigid darkness. Eventually, it will cross the heliopause, the boundary where solar wind gives way to interstellar medium, and resume its journey through the galaxy's spiral arms. Thousands of years from now, tens of thousands, millions, 3I Atlas will drift between the stars, its brief encounter with our solar system a footnote in a journey measured in cosmological timescales. Perhaps it will encounter another star system, be captured into orbit or perturbed into different trajectory. Perhaps it will wander forever through the galactic void, a frozen relic from a stellar system that may no longer exist. The scientific legacy of 3I Atlas is already substantial and will continue growing as researchers analyze the accumulated data. This was the third interstellar object we've confirmed, but it's the first that showed clear cometary activity combined with such unusual chemistry and properties. Every interstellar visitor teaches us about conditions in other stellar systems. The materials present, the formation processes, the chemistry that varies from star to star based on metallicity and history. 3I Atlas's high CO2 content. Unusual nickel signature and large size all provide clues about its birthplace billions of years ago. The technical achievements are noteworthy too. The rapid response observing campaigns, the coordination between space agencies and ground-based facilities, the application of cutting-edge spectroscopy and imaging, all of this improves our capability to study future interstellar visitors. And there will be future visitors. Statistical models suggest interstellar objects pass through the inner solar system regularly, maybe one per year on average. Most go undetected because they're faint or fast-moving or positioned, where our surveys aren't looking. But as our detection capabilities improve, we'll spot more of them. The Vera Rubin Observatory, currently under construction in Chile, will begin operations in 2025 with a 8.4-meter telescope and the largest digital camera ever built, 3.2 gigapixels. It will survey the entire visible sky every few nights, detecting faint moving objects that previous surveys would miss. When Rubin comes online, the discovery rate of interstellar objects will increase dramatically. We'll build a statistical sample, a population of visitors from which we can draw conclusions about galactic-scale processes. How often are objects ejected from planetary systems? What's the size distribution? How does chemistry vary between different stellar populations? Are there families or groups of related objects suggesting common origins? 3i Atlas is teaching us how to study these questions. The observing strategies that worked, the instruments that proved most useful, the analysis techniques that extracted signal from noise, all of these lessons will apply to future discoveries. And perhaps someday, one of those future visitors will prove genuinely unusual in ways that move beyond speculation into confirmed detection of something artificial. If technological civilizations exist elsewhere in the galaxy, if they send probes to survey other systems, eventually one will pass through ours in an era when our technology is adequate to recognize it. Will that be in our lifetimes? Maybe. Maybe not. The universe doesn't schedule revelations for our convenience, but knowing it's possible, knowing we're developing the tools to make that detection if it happens, adds purposeful urgency to astronomy that extends beyond pure curiosity. For now, 3i Atlas remains the fascinating interstellar comet. It's always been unusual enough to generate debate, normal enough to resist definitive categorization as anything other than natural. And that ambiguity, that persistent uncertainty, is perhaps what makes it most memorable. The debate about 3i Atlas's nature reveals something fundamental about how science progresses when confronted with unusual data. It's not a simple binary between believers and skeptics. It's a spectrum of perspectives, each grounded in legitimate reasoning but weighted differently, based on individual assessment of evidence quality and prior probabilities. On one end sits the mainstream consensus. 3i Atlas is an interstellar comet, unusual in several respects, but ultimately explicable through natural processes. This view, held by the majority of professional astronomers, emphasizes that comets are diverse and everyone exhibits unique characteristics. Finding an outlier isn't evidence of artificial origin. It's evidence that our sample size of interstellar objects is too small to characterize the full distribution. Dr. Daryl Seligman, planetary scientist who led several studies on 3i Atlas, represents this perspective clearly. Numerous telescopic observations demonstrate classical signatures of cometary activity. We see outgassing. We see a coma composed of expected molecules. We see behavior consistent with icy bodies responding to solar heating. The natural explanation for each anomaly draws from well-established comet physics. The ecliptic alignment could result from selection bias. We're more likely to detect objects traveling in the plane where our survey telescopes focus. The anti-tail could be asymmetric outgassing from a rotating nucleus. The large size could be statistical variance. We've only detected 3 interstellar objects, insufficient data to meaningfully constrain size distribution. The unusual chemistry, high nickel, high CO2, could reflect formation conditions in a stellar system with different metallicity than our own. Stars vary in chemical composition based on their formation history. Older stars have less heavy element content. Younger stars incorporate materials from previous stellar generations. 3I Atlas might have formed around a star with unusual nickel abundance, perfectly natural given galactic chemical evolution. The perihelion survival without major fragmentation could result from cohesive structure. Perhaps 3I Atlas is unusually dense or has higher rock-to-ice ratio than typical comets, making it structurally sound enough to withstand thermal stress. The brightness increase could be higher albedo or larger size than initial estimates suggested. Every unusual observation has at least one plausible natural explanation. They're not always simple explanations, sometimes requiring specific conditions or invoking rare scenarios, but they remain within known physics without requiring technological intervention. This is Occam's razor applied responsibly, given competing hypotheses that equally well explain observations. Prefer the simpler one that makes fewer assumptions. It's a comet. Requires only that natural processes we understand produced an object with somewhat unusual but not impossible properties. It's artificial. Requires assuming existence of advanced extraterrestrial civilizations, interstellar travel capability, and motivations to survey our system. Several large, unconfirmed assumptions. The middle ground acknowledges the anomalies as genuinely unusual while maintaining that unusual doesn't equal artificial. Dr. David Jewett, comet expert with decades of experience, notes that every comet surprises us in some way. The more carefully we observe these objects, the more individual variation we discover. This perspective emphasizes that our models of cometary behavior are based on limited samples, primarily from comets that formed in our own solar system. Interstellar comets carry chemistry from other stellar environments exposed to different formation temperatures, different radiation environments over billions of years. We should expect them to be weird by our standards. Finding high nickel concentrations isn't impossible, it's just something we haven't encountered before in our limited sample. That doesn't make it artificial. It makes it a data point that will improve our models once we understand the formation pathway that produces nickel-enriched ice. The radio emissions, natural Mossers, occur in comets. Hydrogen line emission at 1.42 GHz isn't common, but isn't physically impossible under appropriate excitation conditions. Claiming it's artificial communication requires additional evidence beyond single unreplicated detections. This middle perspective treats 3I Atlas as an opportunity to expand our understanding of the range of natural phenomena rather than jumping to extraordinary explanations prematurely. On the other end of the spectrum sits the minority position that we should take seriously, the possibility of artificial origin. This view most prominently advocated by Dr. Avi Loeb of Harvard, and the Galileo Project argues not that 3I Atlas is definitely artificial, but that the clustering of anomalies shifts probability enough to warrant treating the technological hypothesis as worth rigorous investigation, rather than dismissal. Loeb's approach involves Bayesian probability updating. Start with a prior probability, your initial estimate before seeing data. Maybe 1 in a million that any given interstellar object is artificial, reflecting our lack of confirmed evidence for extraterrestrial technology despite decades of searching. Then update that prior based on each piece of evidence. If an observation is more likely under the artificial hypothesis than the natural hypothesis, your posterior probability for artificial origin increases. Do this for each of the 8 anomalies Loeb catalogs for 3I Atlas. Ecliptic alignment slightly more likely if artificial targeting the interesting planetary plane than if natural random arrival direction. Update probability upward, but not dramatically because selection bias could explain it. Anti-tail slightly more likely if artificial propulsive corrections than if natural asymmetric outgassing, though rare. Small upward update. large size more likely. If natural, we just got lucky detecting a rare, large object than if artificial, why build big? Slight downward update or neutral. Unusual chemistry, unclear which hypothesis favors. Could be exotic natural formation, or could be manufactured materials. Neutral. Perihelion survival slightly more likely if artificial engineered durability than if natural, most comets fragment. Small upward update. Brightness anomaly unclear. Could be natural albedo or could be reflective artificial surfaces. Neutral. Radio emissions more likely if artificial deliberate signaling than if natural rare masers. Upward update, but how much depends on signal characteristics. After 8 updates, even if each individual update is small, the cumulative effect could shift probability from 1 in a million to 1 in 1,000 or even higher. Still unlikely, but no longer negligible. Loeb argues that when dealing with potential first contact, even low probability scenarios deserve serious attention if the implications are enormous. Its asymmetric risk assessment being wrong about artificial origin costs us some embarrassment and wasted resources. Being wrong about natural origin, if it actually is artificial, could cost us the opportunity to learn from and potentially communicate with an advanced civilization. Better to investigate thoroughly and be wrong than dismiss prematurely and miss something transformative. Critics of this approach argue it's premature and potentially damaging to science communication. When prominent astronomers suggest maybe aliens for every unusual observation, it undermines public trust in astronomy's ability to distinguish signal from noise. It feeds conspiracy theories and sensationalism. Dr. Chris Lintott from Oxford notes that extraordinary claims require extraordinary evidence, and we're nowhere near that threshold. Suggesting artificial origin without compelling necessity distracts from the genuine scientific value of studying an unusual natural object. There's also concern about the crying wolf effect. If astronomers repeatedly suggest objects might be artificial and repeatedly turn out to be wrong, the public becomes jaded. Then when we actually do detect something genuinely artificial, credibility is depleted and people don't take it seriously. This is valid criticism. Science communication requires balancing honesty about uncertainty with responsibility about how messages are received and amplified. Nuanced statements like, probably natural but worth considering alternatives, become, Harvard scientist says, aliens in viral transmission. The philosophical question underneath this debate is, what's the appropriate threshold for entertaining extraordinary hypotheses? One perspective says, exhaust natural explanations first. Only when you've ruled out every plausible natural mechanism, when the observations are truly impossible to explain without invoking technology, should you seriously consider artificial origin. The counter perspective says, don't wait for impossibility. Consider all hypotheses that might explain the data weighted by probability. Artificial origin might be low probability, but it's not zero, and investigating it doesn't prevent simultaneously investigating natural explanations. Both approaches are defensible. The first prioritizes conservative rigor, avoiding false positives at the risk of false negatives. The second prioritizes comprehensive exploration, accepting more false positives to minimize false negatives. Perhaps the honest conclusion is that this debate reflects healthy scientific discourse. Multiple perspectives, different weightings of evidence, various philosophical approaches to uncertainty. This is how science works when data is ambiguous and stakes are high. What matters is that observations are accurate, analyses are rigorous, and conclusions are proportionate to evidence. 3I Atlas has been observed extensively by multiple facilities. The data is public available for independent analysis. Different researchers will reach different conclusions, and that's okay. Over time, as more interstellar objects are discovered and the sample size grows, patterns will emerge. If 3i Atlas is just unusually but naturally weird, future visitors will show different unrelated unusual features demonstrating that weird is common and doesn't cluster in suspicious ways. If it's actually artificial future objects might show similar anomalies building a pattern that shifts consensus. Science is self-correcting over time through accumulation of evidence. Debates like this one about 3i Atlas are part of that process. They sharpen our thinking, refine our methods, and prepare us for future observations that will ultimately resolve lingering questions. As we contemplate this while drifting toward rest, perhaps what's most remarkable isn't the debate itself, but that we're capable of having it. We can detect objects from other star systems, analyze their chemistry, track their motion with precision, and reason carefully about their nature. That capability built over centuries of scientific progress is an achievement worth celebrating, regardless of whether 3i Atlas is a comet or something more. Let's engage in philosophical speculation about a question humanity has pondered for millennia, but which suddenly feels urgent. If we do make contact with extraterrestrial intelligence, how should we respond? This thought experiment applies regardless of whether 3i Atlas is natural or artificial. Eventually, the universe is vast enough and old enough that contact seems inevitable if civilizations are remotely common. Preparing ourselves intellectually and ethically for that possibility serves value even if it remains hypothetical for our lifetimes. First contact scenarios exist on a spectrum from beneficial to catastrophic, and our response could influence which outcomes occur. The most optimistic scenario imagines benevolent contact visitors who are scientifically curious, ethically advanced, interested in peaceful exchange of knowledge and culture. They arrive not to exploit or conquer, but to meet, to learn, to share. If this describes their nature, our optimal response is welcoming, openness, combined with cautious verification, establish communication, exchange information, learn about their civilization, their technology, their perspective on the universe, but verify claims independently rather than accepting everything uncritically. Trust, but confirm. This approach risks vulnerability, revealing our capabilities, showing our weaknesses, inviting potential exploitation if our assessment of their intentions proves wrong. But it also maximizes potential benefits. Access to advanced knowledge could accelerate our development by centuries. Medical technologies, energy systems, solutions to problems we haven't solved. The gains could be transformative. Historical examples of contact between civilizations at different technological levels provide mixed lessons. Sometimes the encounter was mutually beneficial: trade networks, cultural exchange, technological diffusion. Sometimes it was catastrophic for the less advanced party: colonization, disease, exploitation, genocide. The difference often hinged on relative power and the ethics of the more advanced party. When power imbalances were enormous and the advanced civilization lacked ethical constraints, disaster followed. When power was more balanced or ethics constrained, behavior outcomes improved. We can't know in advance whether extraterrestrial visitors would operate under ethical frameworks that respect our autonomy and rights. We can hope, but hope isn't strategy. The Prime Directive from Star Trek provides one ethical framework: non-interference with less developed civilizations. The idea is that contamination from advanced contact might prevent a civilization from developing, naturally robbing them of the discoveries and struggles that forge cultural identity. If extraterrestrial civilizations follow similar non-interference principles, they might already be present but deliberately avoiding contact until we reach some threshold of development, technological, ethical, or both. The zoo hypothesis suggests we're being observed from distance but not engaged because we're not ready yet. Personally, I find this patronizing. Who decides readiness? What gives advanced civilizations the right to withhold contact based on their judgment of our development? But I acknowledge the underlying concern. Contact could be disruptive, potentially harmful, and caution is defensible. The opposite approach is active engagement, METI messaging to extraterrestrial intelligence. Instead of passively listening for signals, deliberately transmit our own messages, advertising our presence and inviting response. METI is controversial within the SETI community. Critics argue it's reckless to announce ourselves to potentially hostile civilizations. We don't know who's listening. Broadcasting our location and capabilities might invite attention we can't handle. Supporters argue that objections are moot. We've been inadvertently broadcasting for a century through radio, television, radar transmissions that leak into space. Anyone within 100 light years with sufficient sensitivity already knows we're here. Deliberate messaging just makes our signals clearer and more informative. My own view leans toward caution. We're effectively children playing with matches when it comes to cosmic signaling. We don't understand the threat landscape. Broadcasting might be safe or it might be catastrophically stupid. Given uncertainty, defaulting to quiet listening seems prudent until we know more. For 3i Atlas, specifically suppose it were artificial and attempting contact. Should we respond? Several factors would inform that decision. First, verify the signal is genuine and not misinterpretation or artifact. Confirm through independent observations. Establish that communication is actually occurring rather than pattern recognition running wild. Second, coordinate internationally. First contact affects all humanity, not just whichever nation or institution first detects it. Unilateral response by individual actors could commit humanity to positions we haven't collectively agreed upon. The International Academy of Astronautics has protocols recommending exactly this: verify, then consult, then respond with input from global stakeholders. Third, consider content carefully. Initial responses should be simple, mathematical, unambiguous prime numbers, geometric patterns, periodic table, basic arithmetic. Establish that we understand the communication is intentional and that we can engage in structured information exchange. Avoid revealing information that could be exploited. Details about our biology, our psychology, our weaknesses, our technological limitations. Start with information that demonstrates intelligence and goodwill without creating vulnerability. Fourth, maintain skepticism throughout. Verify everything. Don't accept claims about intentions or capabilities at face value. Advanced technology doesn't guarantee advanced ethics. A civilization capable of interstellar travel might operate under value systems completely alien to human morality. The darkest scenarios involve hostile contact visitors with exploitative or aggressive intentions. How do we respond if threatened military thinking tends toward defensive preparation? Position assets to monitor and potentially intercept. Develop capabilities to destroy or deflect incoming objects if necessary. Maintain strategic readiness while hoping it's unnecessary. But military response to superior technology is problematic. If they can cross interstellar space, they likely possess capabilities far beyond ours. Attempting military confrontation might be futile or provoke escalation that guarantees our defeat. Better strategy might involve deterrence through demonstration of will and capability combined with clear communication about red lines. We're not helpless. We will defend ourselves if threatened, but we prefer peaceful resolution. Back that message with demonstrated capability. Show that we can track, intercept, and respond to threats even if our technology is inferior. This assumes rational actors who respond to deterrence. It might not work if motivations or decision-making processes are incomprehensibly alien. Another consideration. What if contact is accidental rather than intentional? An automated probe following ancient programming, not representing active civilization at all, or a damaged vessel seeking refuge, or scientific expedition gone wrong. Our response should account for these possibilities. Not every encounter is first contact with active intelligence. Sometimes you're just dealing with artifacts, remnants of civilizations long dead, autonomous systems operating without conscious oversight, natural phenomena misinterpreted as artificial. Responding appropriately requires flexibility, updating assessment as new information arrives, avoiding premature commitment to fixed interpretations. The philosophical question underlying all this: what obligations do we have toward extraterrestrial intelligence, and what obligations do they have toward us? Some argue for universal rights. Any sufficiently complex consciousness deserves moral consideration, regardless of origin. Intelligence, wherever it arises, merits respect for autonomy, freedom from suffering, opportunity to flourish. Others argue rights are human constructs without universal validity. Different species might operate under completely different ethical frameworks. Expecting aliens to respect human rights concepts is anthropocentric projection. I lean toward a pragmatic middle ground. Assume consciousness matters, that suffering should be minimized, that cooperation produces better outcomes than conflict. These principles seem broadly applicable across intelligence types because they arise from game theory and evolutionary stability rather than human-specific cultural constructs, but remain open to discovering that aliens operate under frameworks so different from ours that common ethical ground doesn't exist. In that case, negotiation and mutual understanding become harder, but not impossible. We've dealt with value conflicts throughout human history, between cultures, between religions, between political systems. We've developed methods for coexistence despite fundamental disagreements. Treaties, trade, diplomacy, deterrence. These tools might translate to interstellar context adapted for dealing with beings who think differently than we do. One final consideration: the impact of contact on human civilization, even if purely peaceful. Revealing that we're not alone, that other intelligences exist, would transform philosophy, religion, culture, and science. It would answer the oldest question, are we alone, definitively, and reshape how we see ourselves. Some religions would adapt seamlessly. If God created the universe, why not populate it with multiple intelligent species? Others would face theological crisis. Does revelation apply universally or only to humanity? Science would gain unprecedented opportunities, learning from civilizations that solved problems we're still struggling with. Comparing evolutionary paths, understanding which aspects of consciousness are universal versus contingent on Earth-specific development. But there would be disruption too. Economic systems built on scarcity might face challenges if advanced technology enables abundance. Power structures based on information control would crumble if knowledge suddenly becomes freely available from external sources. Some individuals and groups would thrive in the new paradigm. Others would lose status, resources, or purpose. Managing that transition humanely while maximizing benefits and minimizing harm would be among humanity's greatest challenges. All of this speculation assumes contact occurs in ways that allow deliberate response. Real contact might be sudden, ambiguous, or outside our control. The scenario where we detect a signal and have time to coordinate international response is optimistic. Reality might be messier, unexpected encounters, rapid escalation decisions made under pressure without time for careful deliberation. Preparing intellectually and ethically, now thinking through these scenarios before they're urgent, gives us better chance of responding wisely when contact actually occurs. We may not get everything right, probably won't, but we'll be less likely to make catastrophically stupid mistakes if we've thought about the possibilities in advance. As we contemplate first contact philosophy while settling into evening rest, perhaps the key insight is this approach with humility. We don't know what's out there, what they want, or how they think. Confidence without knowledge is dangerous. Better to acknowledge uncertainty, maintain flexibility, and remember that the universe has surprised us before and will certainly surprise us again. December 2025 represents a critical observational window for 3i Atlas, perhaps the last opportunity for detailed study before the comet fades beyond detection as it recedes into the outer solar system. The geometry favors observers in the southern hemisphere initially. As 3I Atlas climbs higher above the ecliptic plane through early December, it becomes visible in the pre-dawn sky for southern observers: Australia, South Africa, Chile, Argentina. Northern Hemisphere observers will get better views later in the month as the comet's declination shifts. Amateur astronomers with 8-inch or larger telescopes under dark skies should be able to detect 3I Atlas as a faint, diffuse smudge against the background stars. It won't be spectacular, no bright tail visible to the naked eye, no dramatic coma blazing across the sky. Just a modest 11th or 12th magnitude object requiring patience and dark adaptation to observe. But for those who do observe it, there's the profound satisfaction of seeing something that originated beyond our solar system. A visitor from stellar neighborhoods light years away, currently making its one-time passage through our cosmic backyard. Professional observatories have comprehensive campaigns planned. The European Southern Observatory's Very Large Telescope in Chile will conduct spectroscopic observations throughout December, tracking how emission lines change as the comet cools and outgassing diminishes. They're particularly interested in that nickel signature. Does it persist, strengthen, or fade as solar heating decreases? The Keck Observatory in Hawaii will contribute optical and near-infrared observations, measuring the nucleus size through thermal modeling and analyzing the dust properties in the coma. Dust grain size distribution tells you about the comet's formation environment and weathering history. NASA's Hubble Space Telescope has multiple observation slots scheduled. High-resolution imaging will search for signs of fragmentation, discrete chunks that might have separated at perihelion and are now following slightly different trajectories. If fragments exist, Hubble should spot them. The James Webb Space Telescope will conduct its final planned observations of 3I Atlas in mid-December, using its infrared spectrographs to measure carbon monoxide, carbon dioxide, water, and organic molecules as the comet cools. By comparing these December measurements to the August observations, researchers can map how cometary activity varies with solar distance. Ground-based radar won't be useful at this range. 3I Atlas will be too distant for useful radar returns, but optical tracking will refine the orbit to high precision. Every night of observations improves the trajectory calculation, reducing uncertainty about where the comet will be in future months and years. This orbital refinement serves important purposes. If 3I Atlas's path shows any deviations from purely gravitational predictions, non-gravitational accelerations from outgassing, or hypothetically propulsion, those deviations will become apparent as measurements accumulate. Natural comets routinely show non-gravitational forces. Gas jets acting like rocket exhaust push the nucleus in directions that gravity alone wouldn't produce. These forces are small, typically changing velocity by meters per second over months, but they're detectable and must be accounted for in precise orbit calculations. For 3I Atlas, distinguishing between natural outgassing forces and hypothetical artificial propulsion requires careful analysis. Outgassing forces correlate with solar heating. They peak near perihelion and decline with distance. Propulsive forces could occur at any time independent of solar distance and might show structured patterns suggesting deliberate maneuvers. So far, no evidence of non-gravitational accelerations beyond what outgassing would produce has been confirmed. The comet follows predictions within observational uncertainties, but December's observations will tighten those uncertainties, making any deviations easier to detect. Another focus will be monitoring for any changes in brightness or coma morphology. Natural comets can undergo outbursts, sudden brightening events from subsurface ice pockets that explosively decompress, creating temporary surges in gas and dust production. These outbursts are unpredictable and reveal information about internal structure. If 3I Atlas experiences outbursts in December that would argue for natural origin, artificial objects don't randomly explode. Steady, predictable behavior would be more ambiguous, consistent with either natural comet or artificial object. The radio astronomy community will maintain watch as well. While the hydrogen line emissions detected by Parker Solar Probe at perihelion haven't been replicated, observers will monitor for any additional radio signals as 3I Atlas passes closest to Earth. The Allen Telescope Array in California. Part of the SETI Institute's search for extraterrestrial intelligence can be directed at 3I Atlas for extended observations across a wide range of radio frequencies. If deliberate transmissions are occurring, sustained monitoring increases detection probability. The Breakthrough Listen project, funded by Yuri Milner's Breakthrough Initiatives, has also allocated observation time on major radio telescopes to examine 3I Atlas. This project, announced in 2015, represents the most comprehensive SETI search ever undertaken, using some of the world's most sensitive radio telescopes to search for artificial signals. If any narrowband structured radio emissions are detected during December, it would be extraordinarily significant. Not proof of artificial origin by itself, natural masers exist, but certainly worthy of intense follow-up and analysis. China's 500-meter aperture spherical telescope. FAST, the world's largest single-dish radio telescope, could contribute observations if Chinese astronomers choose to target 3I Atlas. FAST's sensitivity is unmatched for detecting faint radio signals, though its fixed dish limits which sky regions it can observe as Earth rotates. Beyond professional astronomy, the global amateur community represents important observational capacity. Thousands of skilled amateurs with capable equipment contribute to astronomy, regularly discovering comets, tracking asteroids, monitoring variable stars, and capturing rare transient events. For 3I Atlas, amateur observers provide continuous coverage across time zones and weather patterns. While individual amateur telescopes may not match professional sensitivity, the aggregate network offers something professionals can't: near continuous monitoring that catches short-lived phenomena that scheduled professional observations might miss. Several online platforms coordinate amateur observations. The Association of Lunar and Planetary Observers, the American Association of Variable Star Observers, the International Occultation Timing Association, and others. These networks have proven valuable in past cometary observations, catching outbursts and fragmentation events that professional telescopes weren't watching at the critical moment. For 3I Atlas in December, amateur contributions will supplement professional data, filling gaps and providing independent verification of reported phenomena. Science benefits from multiple independent observers confirming observations before accepting them as genuine rather than artifacts or errors. As December 19th approaches, the date of closest approach to Earth at 269 million kilometers, public interest will likely surge. News coverage tends to peak around closest approach dates, even though the comet will look essentially the same for weeks before and after that geometric milestone. Educators have an opportunity here. Schools could organize viewing events teaching students about interstellar objects, orbital mechanics, and astronomical observation techniques using 3I Atlas as a real-world example. The comet's faintness means students won't see much, but the experience of observing something from beyond our solar system can spark lasting interest in astronomy. Planetariums and science centers might host public programs discussing 3I Atlas, explaining what makes it unusual, addressing questions about whether it might be artificial, and providing broader context about comets and the search for extraterrestrial intelligence. The key message for public communication is balanced honesty. 3I Atlas is genuinely interesting and unusual, worth serious scientific study, but most likely natural. The artificial hypothesis remains possible but unsupported by definitive evidence. We should keep watching because more data improves understanding regardless of which explanation proves correct. After the December 19th closest approach, Sky Atlas will gradually fade as distance increases. By January 2026, it will be beyond magnitude 13, challenging for amateur observers. By February, magnitude 14 or fainter, accessible only to larger professional telescopes. Through spring 2026, as it approaches Jupiter, it will dim further until only the most sensitive instruments can track it. Eventually, probably by mid-2026, 3i Atlas will fade below detection threshold even for professional surveys. It will continue its journey unseen, a dark, frozen nucleus tumbling through space, but beyond our ability to observe. The scientific papers will continue appearing for years. Research takes time, careful analysis of spectroscopic data, modeling of physical processes, comparison with theoretical predictions, peer review, and publication. The full scientific legacy of 3i Atlas won't be clear until perhaps 2027 or 2028, when the bulk of analysis is complete and researchers have had time to synthesize findings. Some questions will be answered definitively: exact chemical composition, nucleus size and shape, rotation period, dust properties, outgassing patterns. These are measurements we can make with sufficient observations. Other questions will remain open: exact origin, system formation conditions, interior structure history before entering our solar system. These require inferences and modeling rather than direct observation, leaving room for uncertainty and continued debate. And the biggest question, natural or artificial, will likely remain unresolved unless additional evidence emerges. Absence of definitive proof for artificial origin doesn't constitute proof of natural origin, but it does make natural origin far more probable simply because that's the baseline expectation, requiring fewer extraordinary assumptions. As we watch December unfold and 3i Atlas makes its closest approach, we're witnessing a rare cosmic event, an interstellar visitor passing through our neighborhood, offering a brief window for study before departing forever. Whether it's a frozen relic from another star system or something more remarkable, it represents connection to the wider galaxy, reminder that our solar system isn't isolated but embedded in larger structures, where objects occasionally migrate between stellar territories. That connection, that reminder of our place in the galactic ecosystem, has value regardless of 3i Atlas's ultimate nature. We're part of something larger than ourselves, participants in cosmic processes that operate on scales dwarfing human experience. And occasionally the universe sends us visitors that make those vast scales tangibly real, observable in our telescopes, trackable in our data, undeniably present in our skies. The story of 3i Atlas isn't just about a comet. It's about humanity's relationship with the unknown, our capacity for wonder and fear, our cognitive biases and scientific rigor, our readiness or lack thereof for contact with whatever lies beyond Earth. Why does this particular interstellar object capture imagination more than Oumuamua or 2i Borisov did? All three are scientifically fascinating, but 3i Atlas generated more public interest, more speculation, more controversy. Understanding why reveals something about our psychology and culture in 2025. Partly its timing. Oumuamua arrived in 2017 when interstellar visitors were novelty. The initial shock of, we detected something from another star system, dominated discussion. By the time 2i Borisov appeared in 2019, the novelty had worn off. It was scientifically valuable but less headline-grabbing. 3i Atlas benefits from the Goldilocks zone of familiarity. We know enough about interstellar objects to have expectations, but not so much that they're boring. And it arrived at a cultural moment when public interest in UAP's unidentified aerial phenomena, extraterrestrial life, and space exploration is particularly high. The UAP hearings in the U.S. Congress in 2023 and 2024, where military personnel testified about unexplained aerial encounters, primed public consciousness for the possibility of non-human intelligence. Whether those UAPs are extraterrestrial technology or misidentifications remains unclear, but the hearings normalized discussing the possibility that we might not be alone. 3i Atlas arrived into that prepared cultural soil. Public imagination was already considering extraterrestrial possibilities, making the leap from unusual comet to maybe artificial easier than it would have been in earlier eras when such speculation was more taboo in mainstream discourse. Social media dynamics amplified the story. Algorithms optimize for engagement, and nothing drives engagement like mysteries, conspiracies, and existential questions about alien life. Posts claiming NASA hiding truth about interstellar probe get far more sharing and commenting than accurate but boring posts explaining cometary chemistry. This isn't inherently evil. People are genuinely interested in these topics, but it creates information environments where sensational speculation spreads faster than careful analysis, where complexity collapses into simplified narratives, where uncertainty becomes twisted into either definite threat or definite hoax, depending on which tribal affiliation you signal. The 3i Atlas discussion revealed these dynamics clearly. Scientists trying to communicate nuanced uncertainty, probably natural but worth investigating, got distorted into either scientists confirm alien probe or scientists covering up alien probe, depending on which narrative communities wanted to promote. This reflects deeper epistemological challenges in modern society. How do we maintain shared understanding of truth when information sources multiply and institutional trust declines? How do we distinguish expertise from opinion when anyone can publish content claiming authority? Science works through peer review replication and gradual consensus building among experts who spend careers studying specialized topics. But public discourse operates on different timescales and different validation mechanisms: virality, emotional resonance, tribal affiliation, charismatic presentation. The gap between how science establishes knowledge and how public consciousness forms beliefs creates friction. Scientists frustrated that careful analysis gets ignored while speculation goes viral. Public frustrated that scientists seem dismissive of interesting possibilities or speak in hedged language that doesn't provide desired certainty. Bridging this gap requires effort from both sides. Scientists must communicate more effectively, acknowledge uncertainty without paralyzing decision-making, and remain open to unconventional ideas, while maintaining rigorous standards for evidence. Public must develop better scientific literacy, understand how probability and uncertainty work, and resist cognitive biases toward pattern finding and confirmation of preferred beliefs. The 3i Atlas case study provides excellent material for teaching these concepts. It demonstrates how genuine mysteries should be approached: gather data, consider multiple hypotheses, update beliefs. As evidence accumulates, remain open to surprise while maintaining skepticism of extraordinary claims. It also demonstrates cognitive biases we should guard against: confirmation bias, seeking information that supports preferred conclusions while dismissing contradictory evidence. People who want 3i Atlas to be artificial focus on anomalies and discount natural explanations. People who want it to be natural focus on conventional explanations and dismiss unusual features. Pattern recognition bias, seeing meaningful patterns in random or ambiguous data. The human brain is extraordinarily good at finding patterns which served evolutionary advantage, but also produces false positives. We see faces in clouds, hear messages in static, find conspiracies in coincidences. Availability bias, overweighting recent vivid or emotionally salient information. Because 3i Atlas is current and unusual, It feels more significant than the thousands of normal comets observed over centuries. Novelty doesn't equal importance, but our brains weight novel information heavily. Dunning-Kruger effect overconfidence from limited knowledge. People with minimal astronomy background sometimes confidently declare, "Three-eye atlas must be artificial, underestimating how much they don't know about cometary physics." Genuine experts, knowing how much remains unknown, express appropriate uncertainty. These biases aren't weaknesses to be ashamed of, they're features of cognition that usually serve us well. But in contexts like evaluating interstellar objects, they lead us astray, unless consciously monitored and corrected. The philosophical question running through all this: what does our reaction to Three-Eye Atlas reveal about humanity's readiness for actual first contact? Optimistically, we demonstrated capacity for rapid global coordination. Observatories worldwide collaborated on observation campaigns. Data was shared openly. Scientists from different nations worked together, analyzing results. This cooperation across borders suggests we're capable of unified response when confronted with genuinely novel phenomena. We also demonstrated healthy scientific debate. Multiple perspectives were represented, from conservative skepticism to open-minded speculation. The discourse, though sometimes contentious, remained largely within bounds of rational argumentation. This is how science should work: competing ideas tested against evidence. But pessimistically, we also demonstrated tribalism, misinformation spread, and failure to maintain nuanced understanding. The discourse fragmented into camps with predetermined conclusions. Facts became negotiable depending on which authorities you trusted. Uncertainty was intolerable. People demanded definite answers even when evidence couldn't support them. If actual first contact occurs, these dynamics would amplify enormously. The stakes would be existential rather than just intellectual. Government responses, military postures, public panic or celebration, religious reactions, all would interact in complex, potentially chaotic ways. Our handling of Three-Eye Atlas provides a dress rehearsal revealing strengths and weaknesses in how we process extraordinary possibilities. We can learn from this, identify failure modes, and hopefully improve before the stakes become truly critical. One encouraging development: the scientific community's willingness to at least discuss artificial origin possibilities rather than dismissing them out of hand. 50 years ago, suggesting that an astronomical object might be artificial would have been career suicide outside dedicated SETI contexts. Today, while still controversial, it's within the bounds of discussable hypotheses if framed carefully and backed by some evidence. This openness to unconventional ideas, combined with maintenance of rigorous evidentiary standards, represents scientific progress. We're becoming better at balancing skepticism with genuine open-mindedness. The Three-Eye Atlas episode also reveals our fascination with cosmic connection. We want to find evidence of other intelligences, other civilizations, other perspectives on the universe. This desire transcends cultural boundaries. People worldwide expressed interest in the possibility that Three-Eye Atlas might be artificial. That universal curiosity about whether we're alone suggests that actual contact, if it occurs peacefully, would be received with more wonder than fear by most people. There would be anxiety, certainly uncertainty about implications, but also tremendous excitement about finally answering the oldest question. Of course, this assumes peaceful contact. If the first signal we receive is demonstrably hostile, reactions would skew toward fear and defensive preparation. But absent clear threat, human curiosity and desire for connection seem to dominate initial emotional responses. As we reflect on these deeper questions, while evening settles around us, perhaps the most important realization is this: Three-Eye Atlas, whether it's a comet or a probe, serves as mirror reflecting humanity back to ourselves. Our reactions reveal our hopes and fears, our cognitive strengths and limitations, our capacity for wonder and our susceptibility to bias. We are in late 2025, a civilization capable of detecting and analyzing objects from other star systems, but still learning how to think clearly about the implications. We have magnificent scientific tools, but sometimes struggle to use them wisely. We're curious and imaginative, but also tribal, and prone to confirmation bias. In short, we're human flawed, but growing limited, but learning imperfect, but improving. And that might be exactly the right state to encounter whatever mysteries the cosmos sends our way. Not perfectly prepared, but willing to try. Not certain of outcomes, but committed to finding out. As December 2025 progresses and 3I Atlas recedes into the outer solar system, what lasting impact will this interstellar visitor leave on astronomy culture and human consciousness? The scientific legacy is already substantial and will continue growing. Every interstellar object we detect and study expands our understanding of planetary system formation, chemical evolution, and galactic dynamics. 3I Atlas has contributed uniquely to this growing dataset. Its large size teaches us about the upper end of the interstellar object distribution. Are massive visitors rare, or are we simply more likely to detect them because they're brighter? As observational cadence improves with next-generation surveys like Vera Rubin Observatory, we'll discover whether 3I Atlas represents an outlier or the tip of an iceberg of large interstellar objects we've been missing. The unusual chemistry high CO2 to water ratio nickel enrichment provides clues about formation environments in other stellar systems. Not every planetary system forms like ours. Some stars have different metallicities, different proportions of rock forming versus ice forming materials, different temperatures at various orbital distances. 3I Atlas carries a chemical signature from conditions we can't recreate in laboratories or observe directly in distant stellar systems. It's an interstellar sample return mission we didn't have to launch. The technical achievements during the observation campaigns will inform future interstellar object studies. We learned which instruments are most valuable for rapid characterization spectroscopy for chemistry, photometry for size, and rotation radar for structure when objects get close enough. We refined techniques for extracting astrometry from objects with extended comas. We demonstrated rapid coordination between ground and space assets. When future visitors arrive, and they will probably more frequently as detection improves, we'll be better prepared to study them effectively during the limited observational windows before they recede beyond detection. The IAWN training campaign scheduled for late 2025 and early 2026 serves this preparation function. By practicing on 3I Atlas, astronomers worldwide will improve their skills for handling future hyperbolic visitors, whether those are natural comets or hypothetical artificial probes. Beyond technical astronomy, 3I Atlas leaves cultural and philosophical legacies. It brought mainstream attention to the reality of interstellar visitors in ways that Oumuamua and 2I Borisov didn't fully achieve. Public awareness of these objects has increased. People who never thought about interstellar space now know that objects migrate between stellar systems, carrying information about the wider galactic environment. This awareness shifts perspective subtly but meaningfully. Our solar system isn't isolated. It's porous part of larger galactic flows, occasionally receiving visitors and presumably occasionally losing objects to interstellar space as planets gravitationally eject comets or asteroids that escape into the void. We're connected to the galaxy in tangible ways, not just abstract theoretical understanding, but observable objects arriving from elsewhere. This connection makes the cosmos feel more immediate, more relevant to daily existence, rather than distant abstractions studied only by specialists. The debate about artificial origin, regardless of resolution, normalized discussing extraterrestrial technology in mainstream scientific discourse. A decade ago, suggesting astronomical objects might be artificial was fringe speculation. Today, while still requiring substantial evidence, it's discussable among respected astronomers without automatic dismissal. This normalization matters for CT and related fields. If we're willing to seriously consider that unusual objects might be artificial, we're more likely to design appropriate detection strategies, allocate resources for follow-up observations, and maintain open-mindedness toward evidence that challenges conventional assumptions. Whether 3i Atlas specifically proves natural or artificial, it has already succeeded in making us think more carefully about how we'd recognize the difference. What signatures would definitively indicate technology? What observations would rule out natural explanations? These aren't just abstract questions anymore, they're practical considerations that informed actual observation planning. The public discourse around 3i Atlas, despite its sometimes frustrating dynamics of misinformation and tribalism, also demonstrated appetite for serious scientific mystery. People are interested in careful analysis, nuanced uncertainty, and gradual evidence accumulation when topics engage imagination. Science communicators learned valuable lessons about how to discuss ambiguous phenomena. What worked? Acknowledging uncertainty, clearly explaining why questions remain open, maintaining humility about limitations of current knowledge. What didn't work? Dismissing speculation without engagement, failing to address why people find artificial hypotheses compelling, speaking only to fellow experts rather than broader audience. Future astronomical mysteries will benefit from these lessons. We're learning how to navigate the space between rigorous skepticism and premature dismissal, between open-mindedness and credulity, between scientific caution and public engagement. Educational institutions have already incorporated 3i Atlas into curricula as a case study for teaching critical thinking, probability, and scientific method. The object provides real-world example of how scientists approach unusual data, test competing hypotheses, and update beliefs as evidence accumulates. Students working through the 3i Atlas case learn about orbital mechanics, spectroscopy, observational astronomy, and statistical analysis. But they also learn softer skills, evaluating source credibility, recognizing cognitive biases, distinguishing evidence from speculation, maintaining intellectual humility while drawing provisional conclusions. These skills transcend astronomy. They're foundational for navigating information-rich environments where truth isn't always obvious and different sources provide conflicting claims. Learning to think clearly about 3i Atlas prepares students for thinking clearly about anything. The long-term scientific questions opened by 3i Atlas will drive research for years.
How common are interstellar objects? What's their size distribution? How does chemistry vary between objects from different stellar populations? Can we ever trace specific visitors back to specific origin systems? These questions motivate theoretical work on planetary system dynamics, observational campaigns, with next-generation telescopes and technological development for improved detection and characterization capabilities. The quest to understand interstellar visitors funds astronomy that benefits science broadly, not just this narrow specialty. And there's the counterfactual consideration: what if future observations reveal something that changes the natural versus artificial assessment? Scientific conclusions should remain tentative when evidence is incomplete. If 3i Atlas performs unexpected trajectory changes as it recedes, or if follow-up analysis discovers features inconsistent with natural formation, the conversation shifts dramatically. This remains unlikely but not impossible. Science must stay open to evidence that contradicts current consensus. The history of astronomy includes numerous examples where unusual observations eventually overturned prevailing theories. Continental drift quasars, pulsars, exoplanets, dark matter, dark energy. All were initially met with skepticism before evidence compelled acceptance. If 3-Eye Atlas ultimately proves more unusual than current evidence suggests, the legacy becomes revolutionary rather than merely interesting. But that outcome requires evidence we don't currently possess. For now, the legacy is more modest, but still significant. Less demonstrated that interstellar visitors can be studied comprehensively with modern instruments. It revealed gaps in our understanding of cometary chemistry. It sparked healthy scientific debate about how we recognize artificial versus natural origins. It engaged public imagination with real cosmic mystery.
It prepared humanity, however imperfectly, for the possibility that someday we might receive visitors we can't explain through natural processes alone. These contributions justify the attention devoted to this object. Not every astronomical discovery warrants extensive observing campaigns and public discussion, but interstellar visitors are rare enough and the questions they raise important enough that comprehensive study serves science and society alike. As 3-Eye Atlas fades from view over coming months, it joins the pantheon of objects that expanded human knowledge and sparked imagination. Halley's Comet bringing regularity to the heavens. Shoemaker-Levy 9 demonstrating cosmic violence. Oumuamua revealing interstellar immigration. 2-Eye Borisov confirming it wasn't unique. Each visitor teaches different lessons. 3-Eye Atlas's lesson might be the universe remains capable of surprise.
Objects arrive that challenge easy categorization, that generate legitimate scientific uncertainty, that force us to think carefully about what we know and what we merely assume. That lesson serves us well as we look toward futures, where astronomical discovery continues accelerating. More interstellar visitors will arrive. More unusual phenomena will be detected. More mysteries will demand investigation. Our handling of 3-Eye Atlas provides template imperfect but improving for approaching these future mysteries with appropriate balance of skepticism and open-mindedness, rigor and imagination, caution and curiosity. The universe waits patiently, full of wonders. We're only beginning to discover, governed by laws we're only beginning to understand. And occasionally it sends us visitors that remind us how much remains unknown, how much adventure awaits in the darkness between the stars, how much we have yet to learn about our place in this vast, ancient, mysterious cosmos we call home.
December 19th, 2025 will come and go. 3-Eye Atlas will pass closest to Earth, a faint smudge in telescopes, for those patient enough to seek it invisible to casual observers going about daily lives unaware of the cosmic visitor sharing our neighborhood for these brief weeks. What we've learned from this interstellar traveler extends beyond spectroscopic data and orbital calculations. We've learned about ourselves, how we process mystery, how we handle uncertainty, how we balance hope and fear when confronted with possibilities that challenge comfortable assumptions. The confirmed facts are these: 3-Eye Atlas is real, interstellar, unusual in several measurable ways, and continuing outbound on trajectory consistent with gravitational predictions. It survived perihelion intact. It showed chemical signatures that differ from typical solar system comets. It brightened more than initially predicted. It produced radio emissions at frequencies that natural processes can explain, but that also trigger our pattern recognition instincts. What remains unknown might never be fully resolved. We may never trace it to specific origin system. We may never definitively prove whether every anomaly has natural explanation or whether some features suggest something beyond our current understanding. We may never know with absolute certainty whether we watched a cosmic snowball pass by or whether we glimpsed something more remarkable. That uncertainty is uncomfortable. Our species evolved to make quick decisions with incomplete information because hesitation could be fatal. Ambiguity triggers anxiety that demands resolution. But some questions don't resolve on timescales we prefer. Science advances through patient accumulation of evidence, gradual refinement of understanding, willingness to live with provisional answers until better data arrives. The universe doesn't owe us closure on our schedule. What we can say with confidence is that 3i Atlas, whatever it ultimately proves to be, connected us to the wider galaxy in tangible way. It came from somewhere else. It carried chemistry forged in another stellar system. It traveled for eons across the interstellar void before entering our solar neighborhood and offering us this brief window for observation. That journey, that connection, has value, independent of whether the object is natural or artificial. We're part of a dynamic galaxy where matter flows between stellar systems, where planetary formation produces debris that migrates across light years, where conditions for life might exist in countless locations, where intelligence might arise in forms we can barely imagine. Understanding our place in this larger context matters. Whether we're alone or accompanied, whether consciousness arose only once or commonly, whether technological civilizations are abundant or vanishingly rare, these questions define how we see ourselves and our significance. 3i Atlas doesn't definitively answer these questions, but it keeps them alive, keeps us wondering, keeps us watching the skies with instruments and imagination, hoping that someday we'll detect something that removes all doubt about whether we're alone. Perhaps that's the most valuable legacy, maintaining wonder. In an age of cynicism and certainty where tribalism often overwhelms curiosity and confirmation bias drowns out genuine inquiry, 3i Atlas reminds us that mysteries remain. Real mysteries, not manufactured controversies, but genuine questions where evidence is ambiguous and answers depend on observations we're still collecting. That sense of mystery, combined with scientific discipline to pursue answers rigorously rather than settling for comfortable assumptions, represents humanity at its best. Curious but careful, imaginative but rigorous, open to surprise but demanding evidence, willing to question authority while recognizing expertise. As we drift towards sleep on this December evening, watching the stars emerge in the darkening sky, we might spare a thought for that distant visitor currently receding from our solar system. Whether it's a frozen relic from alien star or something more remarkable, it reminds us we're embedded in structures vast beyond comprehension, part of stories that began billions of years before we existed and will continue billions of years after we're gone. That vastness could feel crushing, could reduce human concerns to insignificant specks lost in cosmic immensity. But it can also feel liberating. We're part of something larger, connected to processes that transcend individual lives and even species' lifetimes, participating, however briefly, in the grand cosmic dance. And somewhere out there, beyond the light pollution and the atmosphere, beyond the orbit of the moon and the planets, 3i Atlas continues its journey, silent, solitary, carrying whatever secrets it holds back, toward the interstellar void from which it emerged. We watched it pass. We studied it as best we could. We wondered, debated, imagined. And now we watch it go, perhaps to encounter other stellar systems in distant millennia, perhaps, to wander forever between the stars, a cosmic castaway that briefly touched our lives before returning to the darkness. What questions does 3i Atlas leave hanging in the December sky as you drift toward sleep? Will we ever know with certainty whether it was just a comet? If it was artificial, will we recognize the truth before it's too late to respond? If it was natural, what other mysteries await in the vast catalog of phenomena we've yet to observe? And what will we discover when the next interstellar visitor arrives, perhaps next year, perhaps next century, perhaps tonight, while we sleep unaware that something impossible is approaching, something that will change everything we think we understand about our place in the cosmos? The universe keeps its secrets well, but occasionally it offers glimpses, visitors that arrive, unannounced phenomena that challenge explanation, mysteries that resist easy resolution. 3i Atlas is one such glimpse. What it reveals depends partly on the object itself and partly on our ability to observe and interpret correctly. We've done our best with the tools and understanding we possess. The rest belongs to time and continued observation. Sleep well. The stars will still be there in the morning, unchanged by our wondering, indifferent to our hopes and fears, magnificent in their distant brilliance. And somewhere among those stars and directions we cannot yet imagine, perhaps, other civilizations are asking the same questions we ask, looking outward into the darkness, wondering if they too are alone, watching for visitors that might signal they're part of something larger. Perhaps 3i Atlas is their answer, or perhaps our answer still approaches carried on trajectories we haven't calculated, bearing evidence we're not yet equipped to recognize, waiting for the moment when humanity is finally ready to understand what it means to live in a galaxy teeming with wonders we've only begun to discover. Until then, we watch, we wait, we wonder, and we dream of stars.